Hello and welcome to Sleepy Science. The strangest thing about the Milky Way is that you have lived inside it your entire life, yet you have never seen what it truly looks like. Every star above you belongs to a galaxy so enormous that light needs tens of thousands of years to cross it, so hidden that most of its mass cannot be seen, and so ancient that some of its stars were already old before the sun existed. Tonight, across 100 calm and mysterious chapters, you will travel from our quiet neighborhood between the spiral arms toward the crowded galactic center, where stars race around an invisible black hole. You will discover the dark matter holding the galaxy together, the dead stars drifting silently through space, the smaller galaxies being torn apart around us, and the distant future when the Milky Way itself may lose its familiar shape and fade into a darker universe. Before we begin, tell me in the comments where you are listening from and what time it is there. And if these slow journeys through science help you relax, remember to like the video and subscribe to Sleepy Science. Now, allow the world around you to grow quiet. Look inward toward the galaxy surrounding you and let the journey begin. Why you are living inside a galaxy you can never see from the outside. Every image you have ever seen of the Milky Way as a glowing spiral floating in darkness is not a photograph taken from beyond it, but a carefully constructed interpretation of a place no human camera has ever escaped far enough to observe. You are not standing beneath the galaxy as the night sky sometimes makes it seem. You are buried inside it, moving with the sun through one small region of an enormous stellar disk. This creates a strange limitation. You can look across the Milky Way, toward its crowded interior or its quieter outer regions, but you cannot turn around and see the entire structure at once. It is similar to trying to understand the shape of a vast forest while standing between the trees. Nearby trunks block distant ones, mist hides the deeper landscape, and every direction reveals only a narrow portion of the whole. To see our galaxy from the outside, a spacecraft would need to travel far beyond its main disk, reaching a distance so immense that even our fastest probes would require timescales far longer than recorded human civilization. The Voyager spacecraft have crossed the boundary of the Sun's immediate influence, but on the scale of the Milky Way, they have barely moved away from their starting point. The galaxy remains around us in every direction, not as a distant object, but as the environment through which the entire solar system travels. This means humanity occupies an unusual position. We belong to a structure we can study in extraordinary detail, yet we can never simply step back and look at it as we look at Andromeda or other galaxies through a telescope. The familiar spiral image is assembled from measurements, comparisons, and indirect evidence rather than an external portrait. There is something quietly humbling in this. You can know the temperature of distant stars, trace clouds thousands of light years away, and measure motions occurring near the galactic center, yet the home containing all of them remains too large for you to view in a single glance. The Milky Way is not merely an object in your sky, it is the hidden architecture surrounding your life, carrying the Earth, the Sun, and every human memory through space, while revealing itself only piece by piece. The strange reason. The Milky Way looks like a pale band across the night sky. On a truly dark night, far from city lights, the Milky Way does not appear as a majestic spiral with sweeping arms. It looks more like a faint spill of smoke stretched across the sky. That pale band is created by your position inside the galaxy's flattened disk. Most of the Milky Way's stars are arranged within a broad, relatively thin layer, and the solar system lies inside that same layer rather than above or below it. When you look along the plane of the disk, your line of sight passes through a far greater depth of the galaxy than it does when you look away from the plane. You are therefore seeing the combined light of enormous numbers of distant stars packed behind one another. Most are too far away and too faint for your eyes to separate individually, so their light blends into a soft, cloudy glow. The effect is not caused by a single luminous object or a continuous ribbon of material. It is the visual sum of countless unresolved stars, mixed with glowing gas and interrupted by dark clouds of dust. In some regions, that dust creates deep cracks through the pale band, making parts of the Milky Way appear torn or divided. These dark areas are not empty holes. They are dense foreground clouds blocking the starlight behind them. The appearance of the band also changes depending on where you are on Earth, what season it is, and which part of the galactic plane is above the horizon. Some sections look broad and textured, while others are thin and difficult to notice. Artificial lighting can erase almost all of it, which is why many people can live their entire lives without clearly seeing the galaxy that contains them. Yet the faintness is deceptive. You are not looking at something weak or insignificant. You are looking through an immense concentration of stars, whose distances soften their separate lights into one quiet glow. The band across the sky is therefore a lesson in perspective. Great structures do not always announce themselves with brightness. Sometimes an entire galaxy can be present above you, and still appear no more substantial than a trace of pale dust. The supermassive black hole hidden at the center of our galaxy. At the heart of the Milky Way sits an object so massive that millions of suns would be required to equal it, yet it occupies a region far smaller than the scale of the galaxy surrounding it. This object is the supermassive black hole known as Sagittarius A. It lies roughly 26,000 light-years from Earth, in the direction of the constellation Sagittarius, hidden within one of the most crowded and complex regions of the Milky Way. A black hole is not a solid sphere or a tunnel punched through space. It is a region where matter has been compressed so intensely that space-time is curved beyond an invisible boundary called the event horizon. Once anything crosses that boundary, returning to the outside universe becomes impossible, according to our current understanding of physics. Sagittarius A contains about 4 million times the mass of the Sun, but the black hole itself produces no ordinary light. What astronomers study is the environment around it: hot gas, powerful magnetic activity, and matter moving under the influence of an extreme gravitational field. Its existence matters because it reveals that the center of our galaxy is not simply the brightest or most crowded location. It is also a place where gravity reaches conditions impossible to reproduce on Earth. Supermassive black holes are found in the centers of many large galaxies, suggesting that they are deeply connected to the way galaxies form and change, although scientists are still investigating exactly how that relationship began. Sagittarius A does not pull the entire Milky Way inward like a cosmic vacuum cleaner. Its gravity dominates only the region nearest to it, while the motion of the wider galaxy is governed by the combined mass of stars, gas, dust, and dark matter spread across enormous distances. The solar system is far too distant to be in danger from it. Still, knowing that such an object exists at the center of your galactic home changes the emotional shape of the Milky Way. The galaxy is not built around a lamp, a planet, or a visible throne. Its deepest center is marked by darkness, an unseen boundary whose presence is known through the way the surrounding universe responds to it. How scientists know the shape of a galaxy. They are trapped inside. Mapping the Milky Way is like trying to draw the floor plan of a vast city while standing inside one crowded street, with buildings, fog, and distance blocking nearly every clear view. Scientists cannot photograph our galaxy from above, so they reconstruct its form by combining many different kinds of evidence, each revealing a different part of the hidden structure. Radio telescopes are especially valuable because radio waves can pass through regions that ordinary visible light cannot penetrate, allowing astronomers to trace clouds of neutral hydrogen spread across the galactic disk. Hydrogen naturally produces a distinctive radio signal, and by measuring how that signal shifts as the gas moves toward or away from us, researchers can estimate where large clouds are located and how they orbit. Young, bright stars provide another clue because they tend to form inside spiral arms and remain close to their birthplaces for part of their lives. By measuring their distances, astronomers can mark sections of those arms even when the full pattern remains obscured. Some distances are found through parallax, the tiny apparent movement of a nearby star against the more distant background as Earth travels around the Sun. Space observatories, such as Gaia, have measured the positions and motions of enormous numbers of stars with extraordinary precision, turning the sky into a three-dimensional map rather than a flat collection of points. For more distant regions, scientists use stars whose true brightness can be estimated from their behavior, comparing how bright they should be with how faint they appear from Earth. The movement of stars also reveals structure. Groups that share similar speeds and directions may belong to the same spiral feature, stellar stream, or ancient population, even when they are widely separated across the sky. None of these methods gives the entire answer alone. The final picture emerges by layering radio surveys, infrared observations, stellar distances, gas motion, and computer models until one galactic design explains the evidence better than competing shapes. This is how astronomers concluded that the Milky Way is a barred spiral galaxy, with an elongated concentration of stars through its center and several major arm segments extending through the disk. The map is still being refined, and some details remain debated, but that uncertainty is not a weakness. It reveals how science can build reliable knowledge without ever seeing the complete object directly. The shape of our galaxy was not discovered in a single photograph. It was patiently inferred from motion, light, timing, and the quiet geometry hidden within millions of separate measurements. How enormous the Milky Way really is. The Milky Way is so large that the human mind can repeat its dimensions without truly feeling what they mean. Its bright stellar disk is commonly estimated to span roughly 100,000 light-years, while its fainter outer populations and surrounding halo extend much farther, making the galaxy's full boundary difficult to define with a single number. A light-year is not a measure of time, but the distance light travels in 1 year, moving faster than anything with mass can travel. Even at that impossible speed, a journey from one side of the main disk to the other would take about 100,000 years, a beam of light that began crossing the galaxy when early humans were living in the distant past might only now be completing the journey. Ordinary spacecraft make the scale even harder to grasp. At the speeds reached by present-day probes, crossing the Milky Way would not take thousands of years, but hundreds of millions, longer than complex animals have existed on Earth. Yet the galaxy is not simply wide. Its main star-filled disk is comparatively thin, measuring only a small fraction of its width, while a thicker and more diffuse population surrounds it. The Milky Way also contains hundreds of billions of stars by many estimates, although the exact total remains uncertain because faint stars are difficult to count. The distances between those stars are usually immense. If the Sun were reduced to the size of a small grain, the nearest other star would still be many kilometers away at the same scale. This emptiness allows the galaxy to contain an almost unimaginable number of suns, without becoming a crowded solid mass. Its size also changes the meaning of communication. A radio message sent toward a world 10,000 light-years away would need 10,000 years to arrive, and any reply would require another 10,000 years to return. Entire civilizations could rise and disappear before a conversation crossed even part of the galactic disk. The Milky Way therefore cannot be experienced as a single present object. When astronomers observe its distant regions, they see light that began traveling long before human history, meaning different parts of the galaxy are always being viewed at different moments in their past. You live within one connected gravitational system, yet no observer can witness every region as it exists at the same instant. Its enormity is not only a matter of distance, it is a separation in time, knowledge, and possible experience. The Milky Way may be your cosmic home, but it is a home so vast that humanity has explored only the smallest surroundings of one star, leaving nearly all of its territory beyond direct reach. Why most of the Milky Way is completely invisible. What appears in a telescope is not the whole Milky Way, but only the small portion of the galaxy that happens to reveal itself through detectable light. Stars dominate familiar images because they shine, Yet the galaxy contains far more than luminous suns, and much of its material either emits almost no visible light or produces radiation human eyes cannot perceive. Cold hydrogen gas, for example, can remain dark in ordinary photographs while revealing itself clearly at radio wavelengths. Other clouds are best detected through infrared, microwave, ultraviolet, or X-ray observations, which is why astronomers need many different instruments to build a more complete picture. Even objects that do emit visible light can be too faint to notice across great distances. Small, cool stars greatly outnumber bright giants, but they contribute far less to the glowing appearance of the sky. Free-floating planets, dim stellar remnants, and other low-luminosity bodies may drift through the galaxy while remaining extremely difficult to detect unless they pass in front of a brighter source or disturb something nearby through gravity. But the largest invisible component is more mysterious. Measurements of stellar motion show that the Milky Way behaves as though it contains much more mass than we can account for by adding together its visible stars and gas. Objects far from the central regions orbit too quickly to be held by the matter astronomers can see. The leading explanation is a vast halo of dark matter surrounding and penetrating the galaxy. Dark matter does not appear to absorb, reflect, or emit light in the normal way, so no telescope can photograph it directly. Its presence is inferred from gravity, from the speeds of stars, the motion of satellite galaxies, and the way mass shapes the larger galactic environment. This means the bright spiral structure commonly used to represent the Milky Way may contain only a minority of its total mass. The glowing disk is the visible trace of a much larger gravitational system whose dominant substance has never been identified in a laboratory. Calling it dark does not explain what it is. The name simply describes our inability to see it. Scientists have proposed several possible particles, but none has yet been confirmed as the complete answer. The unsettling truth is that the galaxy can be measured with great precision while remaining fundamentally unknown in composition. You are surrounded by a structure whose stars provide the light, but whose unseen material may provide most of the gravitational framework. The Milky Way therefore teaches a difficult scientific lesson. Visibility is not the same as existence, and the most important part of a system may be the part that never announces itself to your senses. What would happen if you traveled toward the center of the Milky Way? Your journey toward the center of the Milky Way would not begin with a sudden wall of fire or an irresistible pull into darkness. It would begin with the sky slowly becoming more crowded. As you left the sun's relatively quiet neighborhood and moved inward, the number of stars around you would gradually increase, filling the darkness with brighter and more complex fields of light. You would cross regions rich in gas, newborn stars, supernova remnants, and enormous molecular clouds cold enough to conceal developing solar systems. Progress would become difficult to observe with ordinary vision, because thick lanes of dust would block large portions of the central galaxy, forcing you to rely on infrared and radio instruments to understand what lay ahead. Closer to the galactic center, the environment would grow more energetic. Stars would pass one another at greater speeds, powerful radiation would become more common, and the chances of encountering violent stellar activity would rise. Yet you would not be pulled helplessly toward the central black hole from thousands of light years away. Its gravity becomes dominant only within the innermost region, where stars follow rapid, sharply curved orbits around an unseen focus. If your spacecraft approached that region, navigation would become increasingly dangerous because the gravitational influence of many densely packed objects would make the environment far less stable than the space near Earth. Hot gas, magnetic fields, and high-energy particles would surround you, while the center itself would remain partly hidden behind layers of intervening material. The most surprising part of the journey might be that there is no single moment when the ordinary galaxy ends and the center begins. The transformation would be gradual, moving from calm stellar suburbs into a crowded cosmic metropolis where creation and destruction occur side by side. Reaching the heart of the Milky Way would not simply take you toward one dramatic object. It would carry you into an entire ecosystem shaped by extreme density, ancient stars, violent births, and gravitational forces that reveal how different your home galaxy can become when you leave its quieter edges behind. How long it takes the Sun to complete one orbit around the galaxy, long before the Sun returns to the same region of the Milky Way, entire species can appear, flourish, and disappear from Earth. One complete journey around the galaxy takes the solar system roughly 230 million years. Although the exact estimate varies because the Sun's path is not a perfect circle and the galaxy's mass is distributed unevenly. Astronomers sometimes call this vast interval a galactic year. During one such year, the Sun travels through changing regions of the galactic disk, while carrying every planet, moon, asteroid, and comet with it. The last time the solar system occupied a broadly similar position in its orbit, the earliest dinosaurs were beginning to emerge. The continents were arranged differently, and no human ancestor existed. Since the Sun formed about 4.5 billion years ago, it has completed only around 20 galactic orbits. That means the entire recorded history of civilization occupies an almost invisible fraction of a single journey. The Sun moves at hundreds of thousands of kilometers per hour relative to the galactic center. Yet the distance it must cover is so enormous that its progress feels motionless from a human perspective. This orbit is also more complicated than a planet circling a single star. The Sun responds to the combined gravitational influence of matter spread across the galaxy, and it can be gently disturbed by spiral structure, nearby stars, and massive clouds encountered along the way. Earth therefore follows the Sun around the galaxy while orbiting the Sun at the same time, producing a layered motion that never exactly repeats. Thinking in galactic years changes the scale of familiar events. Mountain ranges can rise and erode, oceans can open and close, and biological evolution can transform the surface of a planet before its star completes one circuit. You experience time through days and lifetimes, but the Milky Way keeps a slower clock, one in which the history of humanity has not lasted long enough for the Sun to move even a noticeable portion of its immense path. The black holes, wandering silently through the Milky Way, somewhere between the visible stars, objects formed in ancient stellar deaths may be crossing the galaxy without producing any light at all. These are isolated stellar mass black holes, remnants left when sufficiently massive stars collapse, and no companion star remains nearby to feed them glowing material. Unlike black holes in bright binary systems, a solitary black hole may drift through space almost perfectly hidden, because a black hole does not shine on its own. Astronomers expect the Milky Way to contain a very large population of these dark remnants, possibly millions or even tens of millions, although the true number is uncertain because most are extraordinarily difficult to detect. Some may continue along the general motion of the stars from which they formed, while others may have received powerful kicks during uneven supernova explosions, sending them onto unusual paths through the galaxy. The phrase wandering black hole can sound as though such an object is actively hunting planets. But the real danger is far smaller than the name suggests. Space is so widely separated that the chance of one passing close to the solar system is extremely low. The deeper mystery is how you can find an object that absorbs light and has no bright companion. One method is gravitational microlensing. If an unseen black hole passes precisely in front of a distant star from our viewpoint, its gravity can bend and magnify the star's light for months or even years. Careful measurements may also reveal a tiny apparent shift in the background star's position, helping astronomers estimate the mass of the invisible lens. Researchers have identified promising isolated black hole candidates this way, but confirming them is difficult because faint stars and other compact objects can create similar signals. These wandering remnants preserve the final chapter of stars whose light vanished long ago. They may pass through the galaxy for billions of years, detectable only during rare alignments with distant sources. Their silence reminds you that the Milky Way contains not only what is shining now, but also a hidden population of stellar remains, carrying the gravitational memory of suns that no longer exist, the ancient stars that were already old before the sun existed. Some stars shining above you tonight had already survived for billions of years, before the cloud that formed the sun even began to collapse. These ancient survivors are found mainly among the Milky Way's older stellar populations, and many formed more than 11 or 12 billion years ago, when the galaxy was still assembling and the universe contained far fewer heavy elements than it does today. Astronomers recognize them partly through their chemical composition. The earliest universe was dominated by hydrogen and helium, while elements such as carbon, oxygen, and iron had to be manufactured inside stars and scattered outward when stars died. An old star containing very little iron is therefore like a page written near the beginning of galactic history, before many generations of stellar enrichment had occurred. Scientists estimate its age by studying its temperature, brightness, composition, and stage of evolution, then comparing those properties with models of how stars change over time. Some of these stars are low in mass, which is precisely why they have endured. They consume their nuclear fuel slowly and can continue shining for periods comparable to the age of the universe. They are probably not the very first stars, because those primordial giants are expected to have lived briefly and vanished long ago, but they may have formed from gas, touched by only one or a few early stellar explosions. When you observe such a star, you are not merely seeing an old object. You are examining physical evidence from an era before the Sun, Earth, planets like ours, or the chemical ingredients of life had fully accumulated. Its faint light carries a quiet contradiction. Something can appear fragile in the sky while having survived nearly the entire history of the cosmos. Why the Milky Way and Andromeda are moving toward each other, while distant galaxies are generally carried away from one another by cosmic expansion, Andromeda is doing something very different. Its light shows that it is approaching us. The reason lies in the local contest between expansion and gravity. The Milky Way and Andromeda are the two largest members of the local group, a gravitationally connected collection of galaxies that occupies a relatively small region of the universe. At this scale, their mutual gravitational attraction can overcome the tendency of space to expand between distant, unbound systems. Astronomers detect Andromeda's approach through a shift in the wavelengths of its light toward the blue, showing that the distance between the two galaxies is decreasing along our line of sight. But knowing that Andromeda is approaching is not the same as knowing exactly where it will go. Its sideways motion is extremely difficult to measure because the galaxy is about 2.5 million light-years away. And even a tiny uncertainty can produce a very different trajectory over billions of years. The gravitational influence of nearby galaxies, especially the Triangulum galaxy and the Large Magellanic Cloud, can also alter the future paths of both major galaxies. Older descriptions often presented a direct collision as inevitable, but newer analyses using Hubble and Gaia measurements show that the outcome remains sensitive to uncertain motions and masses. A 2024 study found roughly even odds of avoiding a merger within the next 10 billion years, while a 2026 analysis, using updated motion estimates, favored a merger more strongly, but still described the prediction as inconclusive. So the remarkable truth is not simply that two galaxies are approaching, it is that scientists can measure motion across millions of light-years while still acknowledging that the final destination remains unwritten within the limits of present evidence. What the Milky Way-Andromeda collision may look like. Should the Milky Way and Andromeda eventually meet, the event would unfold not as one sudden explosion, but as a transformation lasting billions of years. Long before the first close passage, Andromeda would grow steadily larger in the sky, its broad structure becoming increasingly visible until it dominated a view once occupied by a small, hazy patch. As the galaxies swept past each other, their gravitational fields would pull their disks out of shape, drawing stars and gas into vast curved streams known as tidal tails. The familiar spiral patterns of both systems would stretch, twist, and lose their original symmetry, while compressed gas clouds could trigger new periods of star formation, illuminating parts of the disturbed galaxies with young, bright stars. The two galactic centers might separate after the first encounter, slow under gravitational interaction, and return for additional passages. Each approach would transfer energy through the systems, changing their shapes until the original galaxies could no longer be cleanly identified. Their central supermassive black holes would eventually be carried into the same merged core and could form a binary before combining. An event expected to release powerful gravitational waves rather than a flash visible to ordinary eyes. The final remnant might become a smoother, more rounded galaxy, though its exact structure would depend on the angle, speed, gas content, and orbital path of the encounter. The solar system, if it still exists in recognizable form, could be shifted into a different region of the remnant, giving the future sky an entirely unfamiliar arrangement. Yet no observer would watch the whole process as a single spectacle. Generations of stars would be born and die between its major stages. A galactic collision is therefore less like two objects crashing and more like two ancient landscapes gradually being rewritten by gravity until their former identities survive only in the motions of what remains. Why most stars will not collide when the galaxies merge. The most surprising thing about a galactic merger is that two enormous systems can pass through one another, while almost every star continues on without touching anything. A galaxy may look densely packed in photographs, but those images compress distances so completely that they hide how empty the space between stars really is. Stars are tiny compared with the regions separating them, so even when two stellar populations overlap, the chance of one star striking another remains extremely small. A useful way to understand this is to picture a few grains of sand scattered across an entire city. Then imagine another city-sized pattern of grains moving through it. The two arrangements would cross, but direct impacts would be rare. Gravity, however, would still reshape everything. Stars could be pulled onto wider or narrower paths. Some might be thrown far from their original neighborhoods, and entire groups could be rearranged as the combined gravitational field changes. Gas clouds behave differently because they are broad and diffuse rather than compact like stars. They can collide, compress, heat up, and sometimes begin forming new stars. Planetary systems might also experience altered galactic surroundings without suffering a direct stellar encounter. This distinction matters. A galaxy merger can be violent on the scale of structure while remaining surprisingly quiet on the scale of individual stars. The grand patterns are disturbed, yet most suns simply continue through the darkness on new trajectories. What appears from afar to be a collision is therefore not a crash in the ordinary sense, but a slow gravitational reorganization of billions of separate journeys. Why the iron in your blood came from earlier generations of stars. Every breath of oxygen carried through your body depends on atoms that did not exist when the universe first began. The iron inside hemoglobin allows your red blood cells to bind oxygen, but the early cosmos contained almost none of it. After the Big Bang, matter was made mostly of hydrogen and helium, with only tiny amounts of a few lighter elements. Iron had to be created later through stellar evolution. Inside massive stars, increasing pressure and temperature allow lighter atomic nuclei to combine into heavier ones through a long sequence of fusion reactions. This process can eventually build an iron-rich core, but iron marks a turning point because fusing it does not release the energy needed to support the star. When such a star can no longer resist gravity, its core collapses and the resulting explosion can scatter newly made elements into surrounding space. Another major source of iron comes from white dwarfs in certain binary systems. If a white dwarf becomes unstable and explodes as a Type Ia supernova, it can produce and distribute enormous quantities of iron group elements. Over billions of years, these stellar remains mixed with interstellar gas, enriching the clouds from which later stars and planets formed. The material that became Earth already contained the chemical legacy of many earlier stellar lives. Iron entered the young planet, became part of its interior and surface, passed through rocks, oceans, organisms, and food chains, and eventually became part of you. This does not mean your blood contains something merely similar to stardust. Its iron atoms are genuine products of ancient cosmic events, a substance now performing a quiet biological task inside your body was once forged under conditions powerful enough to destroy a star, turning every heartbeat into a small continuation of galactic history. Where the solar system is located inside the Milky Way, you are not near the center of the Milky Way, nor are you drifting at its outermost edge. The solar system occupies a relatively calm middle region within the galaxy's broad disk. It lies in a smaller feature commonly called the local arm or Orion spur, positioned between two larger spiral structures. This location places the Sun among ordinary stars, clouds, and scattered star-forming regions, rather than inside the intensely crowded central bulge or the sparse, ancient halo surrounding the disk. The solar system is also close to the galaxy's midplane, although not perfectly aligned with it, and it moves through a local cavity of unusually thin, hot gas known as the local bubble. That bubble was probably shaped by several supernova explosions in the geological past, leaving the Sun inside a low-density region bordered by denser interstellar material. Our location affects what you see in the sky. Looking along the disk reveals rich star fields and dark clouds, while looking above or below it offers a clearer view toward intergalactic space. It also means the constellations visible from Earth are not a universal pattern. From another part of the galaxy, familiar stars would shift into completely different arrangements because the sky is shaped by local perspective. The solar system's address is therefore not simply a point on a diagram. It is a moving environment with its own gas, radiation, nearby stars, and history. You experience the Milky Way from one modest neighborhood within a structure far too large to perceive all at once. And every map of the galaxy begins from that unavoidable fact. The observer is not outside the system, but located within one small and temporary corner of it. The Orion Spur, our small neighborhood inside the galaxy. The name Orion Spur makes our galactic neighborhood sound like a minor branch that barely deserves a place on the map. But modern measurements suggest it is more substantial and complicated than that simple label implies. For many years, astronomers pictured it as a short bridge between larger spiral arms, partly because mapping a structure from within it is difficult. The breakthrough came from studying natural microwave beacons called masers, which form around regions where massive stars are being born. Radio observatories can measure the tiny apparent shift of these masses as Earth changes position during its orbit, allowing their distances to be determined without relying only on how bright they appear. When researchers began placing these star-forming regions on a three-dimensional map, the local arm emerged as a long, active structure with a shape and orientation resembling a genuine spiral arm segment, rather than a random collection of nearby stars. It may stretch for more than 16,000 light-years and could be a branch connected to one of the neighboring major arms, although its exact relationship to the wider spiral pattern is still being refined. The word Orion comes from the prominent stellar associations and nurseries seen in that direction, but the structure contains far more than the familiar Orion Nebula. It includes numerous molecular clouds, clusters, and vast regions where gas is slowly being transformed into new suns. This means your galactic neighborhood is not a fixed row of stars. It is a living corridor of matter shaped by gravity, shock waves, stellar winds, and repeated generations of star formation. Some of the bright young stars now outlining the arm will die long before the Sun, while quieter stars will remain after the arm's present appearance has changed. Even the arm itself is not a permanent object moving as one solid piece. Its stars and clouds follow their own paths through the galaxy, temporarily gathering into a recognizable pattern before continuing onward. What you call your cosmic neighborhood is therefore less like a street built from stone and more like a slowly changing current, carrying unrelated objects together long enough for observers inside it to give the pattern a name. Why the Milky Way is moving through space. even though we cannot feel it. Nothing beneath your feet is truly at rest, yet your body receives almost no hint that the entire Milky Way is traveling through the universe. The reason is that motion by itself does not create a sensation. You feel changes in motion, acceleration, braking, turning, vibration. But a steady shared velocity can remain completely unnoticed. Inside a smoothly moving aircraft, a dropped object falls toward the floor rather than flying toward the back, because you, the air, the object, and the aircraft already share the same forward motion. The same principle applies on a far greater scale. Earth carries you around the sun. The sun participates in the rotation of the Milky Way, and the galaxy moves as part of the local group. Yet nearly everything around you shares these motions. There is no cosmic wind pressing against your body, and no universal floor sliding beneath the galaxy. In modern physics, movement must always be described relative to something else. Compared with nearby galaxies, the Milky Way has one velocity. Compared with the ancient cosmic microwave background, the local group has another. Measurements of that background reveal a subtle temperature difference across the sky caused by our motion, allowing astronomers to estimate that the local group is traveling at roughly 600 kilometers per second relative to this large-scale cosmological reference. This movement is not a random drift. Matter across the universe is distributed unevenly, so galaxy groups respond to the combined gravitational influence of clusters, superclusters, and enormous underdense regions. The Milky Way is being carried through a landscape whose shape can only be inferred from the motions it produces. Yet even these descriptions do not reveal an absolute state of rest, because physics provides no privileged viewpoint from which the entire universe can be declared motionless. You feel stationary because your senses evolved to detect nearby changes that affect survival, not smooth movement shared with a galaxy. The chair beneath you appears still, but stillness is only a local agreement between objects traveling together, a quiet illusion created when everything close enough to matter is moving almost as one. How different the night sky would look near the galactic center. Move the Earth into the innermost regions of the Milky Way, and the first thing you would lose might be the darkness that gives our present constellations room to exist. Near the galactic center, stars are packed far more densely than they are around the Sun, with some central regions containing up to 1 million times as many stars within the same volume. Instead of waiting several light years to reach the nearest neighboring sun, you might find stars separated by only a fraction of a light year. The sky would therefore contain an extraordinary number of bright points, many close enough to show noticeable movement across human timescales. Familiar constellations such as Orion or the Big Dipper would vanish because they are accidental patterns created from Earth's present viewpoint. In their place would be a crowded, changing canopy in which separating one pattern from another might be almost impossible. The pale Milky Way band would also lose its familiar meaning. From our current location, it marks the direction of the galactic disk, but within the dense central bulge, stars would surround you in a much thicker distribution, spreading the galactic glow across a larger portion of the sky. Some directions could appear astonishingly rich, while other regions would remain dimmed by intervening material, preventing the view from becoming a perfectly uniform ocean of light. The stellar population would also feel different. Ancient red giants would share the sky with compact remnants, and in certain central regions, young massive stars born under conditions more extreme than those near the sun. Nights might be brighter, but they would not necessarily resemble daylight. The total appearance would depend on your exact distance from nearby stars, the amount of obscuring material, and the brightness of the local population. More importantly, the sky would no longer feel stable. Close stellar passages would slowly redraw it, and bright stars could change their positions noticeably over generations, rather than remaining nearly fixed throughout recorded history. What you consider a peaceful night sky is therefore not the standard face of the galaxy. It is the view granted by one relatively uncrowded location, where darkness separates the stars enough for the human mind to connect them into stories. Why we cannot see the center of the galaxy with ordinary light. The heart of the Milky Way is not hidden because it is too faint, but because an enormous curtain of dust stands between it and your eyes. Ordinary visible light travels easily through empty space, yet it is scattered and absorbed by tiny grains mixed through the galaxy's disk, especially along the long line of sight toward the center. These grains are made from materials such as silicates and carbon-rich compounds, released and reshaped through generations of stellar activity. Individually, they are microscopic, but spread across thousands of light years, they become powerful enough to block almost all the visible light coming from the central regions. If the dust were suddenly removed, the area around Sagittarius would appear far richer and brighter than it does from Earth, revealing dense fields of stars now concealed behind dark lanes. Astronomers overcome this obstruction by observing wavelengths that interact with dust differently. Infrared light can pass through much of the material that defeats human vision, allowing telescopes to reveal warm stars, glowing clouds, and crowded structures near the center. Radio waves penetrate even more effectively and can trace cold gas, magnetic activity, and compact sources that remain completely invisible in ordinary photographs. X-rays, meanwhile, expose extremely hot gas and energetic events occurring around dense stellar remnants. Each wavelength acts like a different sense, revealing a layer the others cannot reach. This is why the galactic center does not have one single appearance. It changes depending on the kind of light used to examine it. A visible light telescope sees darkness, an infrared telescope sees stars, a radio telescope hears structure, and an X-ray observatory detects violence. The limitation, then, is not in the center itself, but in the narrow range of radiation your eyes evolved to perceive. What seems absent may simply be speaking in a form you were never built to notice, reminding you that the universe is always larger than the small window through which you first encounter it. Sagittarius A, the quiet giant at the heart of the Milky Way. Giant with the power to tear matter apart, sits at the center of the Milky Way, yet most of the time it behaves with surprising restraint. Sagittarius A is considered quiet because it consumes very little of the material available around it, compared with the intensely active central black holes found in quasars and other energetic galaxies. Gas does drift into the central region, arriving from stellar winds and nearby clouds, but only a small fraction appears to reach the point where it can release enormous amounts of energy. Much of it may be heated, redirected, or blown outward before falling deeply enough to feed the black hole efficiently. This makes Sagittarius A extraordinarily dim for an object of its mass. If it were accreting matter at a much higher rate, the galactic center could shine with tremendous brilliance across many wavelengths, and the environment around it would be far more hostile. Quiet, however, does not mean inactive. Astronomers observe sudden flares in infrared and X-ray light, sometimes growing much brighter for short periods before fading again. These bursts may occur when magnetic fields reconnect in the hot plasma near the black hole, rapidly accelerating particles, or when small clumps of matter move through the turbulent inner flow. The region constantly changes, but it does so like a sleeping animal shifting in the dark, rather than a continuously roaring engine. There is also evidence that the center may have been more active in the past. Vast structures and energized gas elsewhere in the galaxy suggest that stronger episodes may have occurred millions of years ago, when more material reached the central region. Sagittarius A therefore offers a rare opportunity to study a supermassive black hole in a low-feeding state, revealing what happens when enormous gravitational power exists without being fully expressed. Its silence is not emptiness, it is stored possibility, a reminder that the most powerful object in a system does not always need to dominate it visibly. The stars orbiting, incredibly close to Sagittarius A. One of the strongest proofs that an unseen massive object occupies the galactic center comes from stars that race around what appears to be empty space. These stars, often called S-stars, move through the central region on tight, elongated paths that can be followed over years and decades. The best-known example is S2, a hot, bright star that completes an orbit in about 16 years. During its closest approach, it passes within roughly 120 astronomical units of Sagittarius A, far closer to the black hole than most people expect a normal star could survive. It reaches speeds of several thousand kilometers per second, moving so rapidly that its position changes measurably within a short observing period. Tracking such a star requires exceptional precision because the galactic center is distant, crowded, and obscured. Yet long-term infrared observations have allowed astronomers to map its orbit in remarkable detail. That orbit reveals how much mass must be concentrated inside a very small volume. If the central mass were spread among ordinary stars or dark remnants, the cluster would be unstable and would not produce the clean orbital behavior that scientists observe. A supermassive black hole provides the most convincing explanation. These stellar paths have also become laboratories for testing Einstein's description of gravity. As S2 passes through the strongest part of the gravitational field, its light changes in a way predicted by general relativity, and the orientation of its orbit slowly shifts rather than tracing the same closed ellipse forever. The stars are not being swallowed because their trajectories remain outside the event horizon, just as a comet can pass close to the Sun without falling into it if its speed and direction carry it onward. Yet their lives are shaped by an environment unlike anything near Earth, where gravity turns motion itself into evidence. By watching a single point of light complete its long curve, astronomers can weigh an object that cannot be seen and test physical laws under extreme conditions. The star becomes a moving needle on a cosmic instrument, tracing the shape of invisible gravity and showing that even darkness can leave a precise signature. Why the Milky Way's central black hole is surprisingly calm. Feeding a black hole is far more difficult than simply dropping matter toward it, and this hidden difficulty helps explain why the Milky Way's central giant remains strangely quiet. Sagittarius A is surrounded by massive stars that continuously release gas through powerful stellar winds, so the black hole is not living in a completely empty environment. Yet approaching gas usually carries sideways motion, causing it to circle rather than fall directly inward. Before it can cross the event horizon, it must lose much of this motion, shed energy, and move through an extremely hot, turbulent plasma where magnetic fields twist, reconnect, and redirect the flow. Most of the available material never completes that journey. Some passes around the black hole, some becomes heated enough to resist falling farther, and some may be expelled through winds before reaching the deepest region. Astronomers describe this as an inefficient feeding system. Matter enters the black hole's wider gravitational territory, but only a tiny portion arrives at the final boundary. The gas that does approach is also too thin to form the brilliant, dense accretion disk seen around active galactic nuclei, where large supplies of matter convert gravitational energy into intense radiation. Recent observations have strengthened the idea that Sagittarius A is not simply failing to capture fuel. Its surrounding flow may actively push part of that fuel away. Evidence from ALMA and the Chandra X-ray Observatory points to an outflow or wind emerging from the central region, helping clear or heat nearby gas and further limiting the supply. This creates a kind of natural regulation. The little activity that occurs can make future feeding even harder. The black hole is therefore calm, not because its gravity is weak, but because gravity alone does not guarantee a meal. Matter must arrive with the right motion, density, and ability to release energy, and the environment around Sagittarius A rarely provides those conditions efficiently. Its quietness teaches you something unexpected about cosmic power. Even the strongest gravitational pull in the galaxy cannot consume what the surrounding physics refuses to deliver. The giant bubbles extending above and below the Milky Way. An invisible hourglass towers through the Milky Way, with two enormous lobes rising from opposite sides of the galactic plane, and stretching across a distance comparable to half the galaxy's bright width. These structures are known as the Fermi bubbles because they were clearly identified in data from NASA's Fermi Gamma Ray Space Telescope in 2010. Each bubble extends roughly 25,000 light-years from the central region, yet no human standing under a dark sky could see them because they glow mainly in gamma rays, the most energetic form of electromagnetic radiation. They are not empty cavities with solid walls. They appear to contain high-energy particles moving through thin gas and interacting with radiation and magnetic fields, producing a broad glow with surprisingly sharp outer boundaries. Their shape suggests that an enormous release of energy once pushed material away from the center of the galaxy in two opposite directions, where resistance was lower above and below the dense disk. The source of that energy is still debated. One possibility is that Sagittarius A experienced a much more active feeding episode in the past and launched jets or powerful winds that inflated the bubbles. Another is that intense star formation near the galactic center produced many supernovae and stellar winds whose combined force drove a large-scale outflow. Different observations support parts of both pictures, and the true history may involve more than one episode or mechanism. The bubbles also connect to structures seen at other wavelengths, including X-ray features and a microwave haze, suggesting that the same ancient activity may have left several overlapping signatures. Their relatively clean edges indicate that the event was organized on a galactic scale rather than being a random collection of unrelated explosions. Yet their precise age, internal particle population, and method of formation remain active areas of research. The Fermi bubbles reveal that a galaxy can preserve the aftermath of violence long after the original event has faded, turning empty-looking space above and below its disk into a vast record of energy that the human eye was never designed to read. The invisible dark matter, halo surrounding the Milky Way. The largest part of the Milky Way may be a structure that has never appeared in any photograph. Far beyond the bright disk, the central bulge, and the faintest scattered stars lies an enormous dark matter halo surrounding the galaxy like a deep gravitational atmosphere. It is called a halo because models suggest a broad, roughly rounded distribution rather than a thin spiral shape. But astronomers do not assume it is a perfect sphere. Its true form may be slightly stretched, uneven, or disturbed by past encounters. And determining that shape remains difficult because dark matter produces no confirmed light signal of its own. Scientists instead trace its influence using objects that travel through the outer galaxy. Distant globular clusters, satellite galaxies, and long streams of stars act like test particles moving within an unseen landscape. Their speeds, directions, and curved paths reveal how much hidden mass must exist and where its gravitational pull is strongest. Researchers can also estimate the halo by asking how fast an object would need to move to escape the Milky Way entirely. If the galaxy consisted only of the matter visible in its disk, many remote objects would not move as though they remained connected to it. The halo likely reaches several times farther than the main stellar disk, making the luminous Milky Way resemble a small inner structure embedded inside a much larger invisible system. It may also contain smaller concentrations called subhalos, remnants of the hierarchical process through which galaxies are thought to grow by gathering material and absorbing smaller systems. Some of these subhalos may contain faint satellite galaxies, while others could remain almost completely dark. The total mass of the halo is still uncertain because astronomers must infer it from limited traces, and different assumptions about the motions of distant objects can produce different estimates. Even so, the evidence strongly suggests that dark matter accounts for most of the Milky Way's mass. The galaxy you recognize by its stars may therefore be only the illuminated center of its true body, raising a quiet but profound question. When the visible structure is the smaller part, should it still be considered the galaxy itself, or merely the portion the universe permits you to see? Why the galaxy rotates too quickly for its visible matter? The Milky Way should rotate very differently from the way it actually does, and that mismatch is one of the clearest signs that the galaxy contains more than its light reveals. In a system where most of the mass is concentrated near the center, objects farther away should orbit more slowly, just as distant planets move around the Sun more slowly than nearby ones. Astronomers once expected the outer regions of galaxies to follow a similar pattern, because the brightest concentration of stars lies toward the inner disk and bulge. But when they measured the motion of stars and hydrogen gas at increasing distances from galactic centers, the expected slowdown did not appear. Instead, orbital speeds remain surprisingly high across large parts of the disk. These measurements are made by examining small changes in the wavelengths of light and radio signals. Material moving toward an observer shifts one way, while material moving away shifts the other, allowing researchers to build a rotation curve showing how speed changes with distance. If visible stars, gas, and dust supplied nearly all the gravitational mass, the curve should rise near the center and then decline beyond the brightest regions. What astronomers observe is far flatter. The outer galaxy behaves as though a great deal of additional mass continues far beyond the places where most of the light is produced. This is not the result of the stars spinning too quickly in the way loose stones fly from a wheel, because a galaxy is not a solid object rotating as one piece. Each star follows its own orbit within the combined gravitational field of everything around it. The puzzle is that this field is stronger in the outer regions than the visible material alone can explain. Similar behavior appears in many spiral galaxies, turning the problem from a local oddity into a repeated pattern across the universe. Some scientists have explored whether gravity itself might behave differently over enormous distances and extremely weak accelerations, but the leading interpretation remains that galaxies are embedded in large distributions of unseen matter. The rotation curve does not show that astronomers understand this hidden component. It shows that something is missing from the inventory. In this sense, the Milky Way's motion acts like a scale weighing an invisible load. You cannot see what is adding the weight, but every orbit responds to it, forcing you to accept that a galaxy can reveal its deepest secret not through what shines, but through what refuses to slow down. How dark matter helps hold the Milky Way together. Dark matter does not bind the Milky Way like glue between stars. It shapes a deep gravitational landscape through which the entire visible galaxy moves. The distinction matters because stars are not fixed to a rigid spiral structure, and dark matter is not thought to form ropes or walls around them. Instead, its distributed mass contributes to the galaxy's overall gravitational potential, influencing which orbits remain bound and how difficult it is for objects to escape. Without that additional mass, the Milky Way would have a shallower gravitational well, and the speeds measured in its outer regions would be much harder to sustain. But dark matter may have played an even more important role before the mature galaxy existed. In the early universe, small variations in density allowed dark matter to gather into growing concentrations under gravity. Because it does not interact strongly with light, it could begin forming these structures without being heated and pushed outward by radiation in the same way ordinary gas can be. Hydrogen and helium then fell into these dark matter concentrations, collided, cooled, and eventually formed the first generations of stars. In this picture, the invisible structure was not added around a finished galaxy. It helped create the conditions from which the luminous galaxy emerged. As the Milky Way developed, its dark matter environment influenced the arrival of gas, the paths of smaller galaxies, and the long-term distribution of stars. It also increased the range of speeds at which objects could remain gravitationally connected to the system. This does not mean dark matter protects the galaxy from every disruption. Stars can still be ejected, satellite systems can still pass through, and the disk can still bend or respond to encounters. The halo provides a large-scale gravitational framework, not perfect stability. Computer simulations that include dark matter are able to produce networks of galaxies and clusters resembling the observed cosmic structure far more successfully than models based only on ordinary matter. Yet a central mystery remains. Scientists can describe what dark matter does gravitationally, while still not knowing what particle or substance produces the effect. It is an unusual kind of knowledge, precise in consequence, incomplete in identity. The Milky Way may owe much of its formation and continued coherence to something no eye has seen and no laboratory has conclusively captured. That possibility changes the meaning of structure itself, because what appears to hold the galaxy together may not be the brilliant population filling its photographs, but the silent foundation beneath every visible orbit. How the Milky Way grew by consuming smaller galaxies. The Milky Way was not born as the finished spiral you would recognize today. It was assembled through a long history of gathering, merging, and absorbing smaller systems. In the early universe, galaxies were generally less massive and more irregular, and growth often occurred hierarchically, with small structures combining to produce larger ones. The Milky Way preserves evidence of this process in the motions and chemical compositions of its oldest stars. Stars that form together tend to share a recognizable mixture of elements because they were created from the same chemically enriched gas. They may also retain unusual orbital patterns long after their original galaxy has lost its separate identity. By combining these chemical fingerprints with precise measurements of stellar motion, astronomers can identify populations that probably did not form inside the Milky Way's original main body. One of the most important examples is commonly called Gaia Sausage Enceladus, the remnant of a substantial dwarf galaxy believed to have merged with the young Milky Way many billions of years ago. Its stars move on strongly stretched orbits and possess chemical patterns that distinguish them from stars formed within the early galactic disk. That ancient encounter likely added a large population to the stellar halo and may have altered the structure of the young Milky Way by disturbing and thickening its early disk. Other proposed merger remnants, such as Sequoia, suggest that several separate systems contributed stars and compact clusters during different periods. Some globular clusters now orbiting the Milky Way may therefore have begun inside galaxies that no longer exist independently. This method of growth continues on a smaller scale today. The Sagittarius dwarf galaxy is gradually being incorporated into the Milky Way, while other satellite galaxies remain gravitationally associated and may influence its future development. To say that the Milky Way consumed these galaxies does not mean they vanished in a single violent moment. Their gas, stars, clusters, and dark matter were redistributed over immense periods, gradually losing their original arrangement while becoming part of a larger system. The galaxy around you is therefore not a single family with one birthplace. It is a layered population assembled from many histories, some native and some inherited. Every ancient star with an unusual chemical signature may carry the memory of a lost galaxy, revealing that cosmic identity is rarely pure. The Milky Way became itself by incorporating what once existed beyond it, and its apparent unity is the final shape of countless smaller stories that gravity refused to keep separate. How the Milky Way tears apart smaller galaxies. A small galaxy can spend billions of years traveling through space, only to be slowly unmade when it comes too close to the Milky Way. The process is called tidal stripping, and it begins because gravity does not pull equally on every part of the smaller galaxy. The side facing the Milky Way feels a slightly stronger attraction than the far side, creating a gravitational stretch across the entire system. If the dwarf galaxy is compact and distant, its own gravity may keep its stars together. But during repeated close passages, the difference in force grows strong enough to loosen stars, gas, and dark matter from its edges. Material is then drawn away in long leading and trailing tails, with some stars moving ahead of the dwarf galaxy along its orbit, and others falling behind. The destruction is rarely sudden. A satellite galaxy may survive many circuits, losing a little more of itself each time until only a dense central remnant remains, or until even that core is dissolved into the Milky Way. The Sagittarius dwarf spheroidal galaxy provides a clear example. It is currently passing through the Milky Way's environment and has already shed enormous quantities of stars, leaving debris that extends across a large part of the sky. The galactic disk can also contribute to the damage. Each passage through the disk exposes the smaller system to a rapid change in the surrounding gravitational field, a disturbance known as disk shocking, which can inject energy into its stars and make them easier to remove. Dense star clusters may survive longer than the diffuse galaxy that once carried them, continuing to orbit after their original home has disappeared. What looks like destruction from one perspective becomes redistribution from another. The stars are not erased. They are separated from the structure that once gave them a shared identity and added to a much larger galaxy. This is how the Milky Way grows without building every one of its stars itself. It pulls apart weaker companions, absorbs their material, and gradually hides the evidence within its own population. Yet the process is never perfectly clean. Motions, chemical patterns, and surviving remnants preserve traces of the lost system, revealing that gravity can dismantle a galaxy while failing to erase its history. The streams of stars wrapped around the galaxy. Across the Milky Way, there are narrow rivers of stars that appear unrelated until their motions reveal that they are traveling together. These stellar streams are the extended remains of star clusters and small galaxies pulled apart by the galaxy's tidal forces. Once a star escapes its parent system, it does not simply scatter in a random direction. It continues along an orbit similar to the one it followed before, while small differences in speed gradually spread the escaped stars into a long, thin formation. Over time, the original cluster or dwarf galaxy may become difficult to identify, but its released stars can wrap around the Milky Way in arcs stretching thousands of light years. Some streams are broad because they came from relatively massive satellite galaxies with stars moving in many different internal directions. Others are extremely narrow, suggesting they formed from compact globular clusters whose stars once moved within a tightly organized system. Astronomers find these structures by searching for stars that share not only a path across the sky, but also similar distances, velocities, ages, and chemical compositions. Precise stellar surveys have transformed this work, revealing streams that are too faint and dispersed to stand out in ordinary images. These formations are valuable because they behave like long test lines placed inside the Milky Way's gravitational field. A stream's bends, gaps, and changes in density can reveal where unseen mass has disturbed it. A close encounter with a massive cloud, a compact object, or a small concentration of dark matter may leave a recognizable scar in the flow of stars. Streams such as GD1 and the tails of Palomar 5 are therefore studied not only as remnants of destroyed systems, but as sensitive detectors of the galaxy's hidden structure. Their paths can help astronomers estimate the shape of the Milky Way's gravitational environment and test whether invisible clumps exist where no luminous object is seen. Eventually, many streams will become harder to recognize as their stars spread farther apart and mix with the wider halo, a process known as phase mixing. For now, they remain readable traces of events that happened long ago. They show that the galaxy carries its past, not in a written archive, but in motion. A stream is history stretched across space, preserved, because stars can forget their birthplace visually while continuing to remember it through the direction in which they move. The ancient globular clusters orbiting the Milky Way. Long before the Milky Way developed its present appearance, immense spherical communities of stars were already forming, and many of them still orbit the galaxy today. These objects are globular clusters, tightly bound swarms that can contain tens of thousands or even millions of stars packed into a region only a few hundred light years across. Unlike the loose open clusters found mainly in the galactic disk, globular clusters usually travel through the halo on large, tilted orbits that can carry them far above and below the plane. Their stars are generally ancient, often more than 10 billion years old, and many contain relatively small amounts of elements heavier than hydrogen and helium. This chemical simplicity reflects the early era in which they formed, before repeated generations of stellar death had enriched the universe with large quantities of heavier material. Yet globular clusters are not perfectly simple populations. Detailed observations have shown that many contain several groups of stars with subtle chemical differences, suggesting that their early histories involved more than one episode of enrichment or formation. Their interiors are also dynamic. Stars continually exchange energy through close gravitational encounters, causing heavier objects to drift toward the center, while lighter stars migrate outward. Some clusters undergo core collapse, becoming extraordinarily dense in their central regions. Collisions and exchanges between stars can create unusual objects such as blue stragglers, which appear younger and hotter than the surrounding population, even though they probably formed through stellar mergers or transfers of matter. Neutron stars and black holes may also remain hidden inside these crowded systems, occasionally revealing themselves through binary interactions. Because globular clusters preserve such old stars in a relatively confined environment, astronomers use them to study stellar evolution, estimate the age of the Milky Way's oldest populations, and investigate conditions in the early galaxy. Their orbits provide additional clues, since some may have formed with the Milky Way, while others may have arrived inside smaller systems that were later disrupted. Each cluster is therefore both a surviving structure and a historical witness. It has endured the loss of countless individual stars, repeated passages through the galaxy, and billions of years of internal change without completely dissolving. When you look at a globular cluster, you are seeing not one ancient star, but an entire society of them, held together long enough to carry a piece of the young universe into the present. Why the Milky Way is a barred spiral galaxy. Hidden behind the crowded stars of the inner Milky Way is a structure that changes the entire architecture of our galaxy. A long, dense bar of stars cutting through its center. A barred spiral galaxy differs from an ordinary spiral because its arms do not continue smoothly all the way into a round central core. Instead, the most prominent arms appear to extend from the ends of this elongated stellar feature. Astronomers suspected the Milky Way had such a bar long before they could map it clearly. Visible light offered little help because intervening material obscured the inner galaxy. So researchers studied infrared observations, star counts, and the motions of gas. They found that the central stars were not distributed symmetrically around the center. One side appeared closer and brighter than the other, exactly as expected if you were viewing a tilted bar from inside the galactic disk. ESA's Gaia mission later strengthened the case by measuring stellar distances geometrically and revealing the elongated structure in 3 dimensions. The bar is not a rigid beam, and its stars are not permanently locked into one straight formation. They follow families of elongated orbits whose combined arrangement maintains the bar's recognizable shape as it rotates. Astronomers think such structures can emerge naturally when a rotating stellar disk develops an instability, allowing a small distortion to grow as stars exchange angular momentum. Once established, the bar can influence regions far beyond its own length. Its gravity can rearrange stellar paths, drive gas away from some locations, and channel material toward ring-shaped or central regions where new stars may form. It may also interact with the spiral pattern, although the exact relationship between the bar and the Milky Way's arms remains an active subject of study. Bars can weaken, strengthen, or change their rotation over cosmic time, meaning the present shape of our galaxy is not necessarily the shape it always had. The Milky Way is classified as a barred spiral, not simply because a bar has been drawn across a diagram, but because millions of stellar motions collectively sustain a vast pattern that no individual star understands or controls. You live inside a galaxy whose central form is maintained by movement rather than solidity, a reminder that the largest structures in nature can look permanent, while being rebuilt continuously by everything passing through them. How the galaxy's spiral arms form without being solid structures. Spiral arm can remain visible for millions of years, even though the material outlining it may be constantly changing. This is the central puzzle of galactic spirals. If every star simply remained inside one fixed arm, the inner part of the galaxy would complete its orbit faster than the outer part. winding the arms more tightly with each rotation until the pattern became almost unrecognizable. Yet spiral galaxies repeatedly display broad, open structures, which means their arms cannot be understood as permanent chains made from the same stars. One influential explanation treats an arm as a moving region of enhanced density, similar to a traffic slowdown traveling along a highway. The congestion has a recognizable location even though individual cars enter it, spend time inside it, and eventually leave. In a galaxy, gravity can gather stars and gas into a denser spiral-shaped region without attaching them to one another. Gas entering such a region may be compressed, increasing the chance that cold clouds will collapse and form stars. Massive young stars shine intensely, but live briefly, so they illuminate the arm near the locations where they were born, making the pattern appear more solid and sharply defined than it truly is. However, astronomers no longer assume that every spiral arm is one perfectly stable density wave, rotating unchanged for billions of years. Observations and computer simulations suggest that some arms may be temporary and recurrent, growing from disturbances in the disk, becoming stronger, breaking apart, and later reforming in a different arrangement. A central bar, passing satellite galaxy, uneven gas distribution, or the galaxy's own gravitational instabilities may all help create or reshape these patterns. Different arms within the same galaxy may not even share an identical origin or lifespan. This is why spiral structure remains an active field of research, rather than a completed explanation found in a single textbook diagram. What matters is that an arm is a pattern produced by collective behavior, not a solid object with fixed edges. It is closer to a wave moving across water than a branch growing from a tree, except the water consists of stars, gas, dust, and gravity, influencing one another across extraordinary distances. When you see a graceful spiral galaxy, you are not looking at a frozen design. You are seeing a temporary order emerge from countless independent motions, a shape that exists because its contents are moving, not in spite of them. Why stars move in and out of the spiral arms. No star receives a permanent address inside a spiral arm, because the arm is not a container that travels through the galaxy, carrying the same population forever. A star follows an orbit determined by the galaxy's gravitational field, while the spiral pattern can rotate, evolve, and sometimes disappear at a different pace. In the classical density wave picture, stars and gas approach a denser region, pass through it, and emerge on the other side, much as vehicles cross a moving zone of heavy traffic. Gas reacts more dramatically than stars because clouds can collide, lose energy, and become compressed, while stars usually pass through without striking one another. Young stars born from that compressed gas temporarily make the arm more visible, but as they age and continue along their paths, they drift into the spaces between arms. This helps explain why the brightest young stellar populations trace spiral patterns more clearly than many older stars do. The real motion may be even more complex, because some spiral arms appear to rotate at nearly the same local speed as nearby stars, rather than maintaining one single pattern speed throughout the disk. Simulations show that stars can be drawn towards such transient arms from both sides and travel alongside them for a time. During this interaction, the arm's gravity can alter a star's orbital energy, moving it closer to or farther from the galactic center, while leaving its orbit relatively circular. This process, called radial migration, allows a star to change its galactic neighborhood without experiencing a violent encounter. The Sun itself may not have formed at precisely its current distance from the center, although reconstructing its original birthplace remains difficult. Migration can mix stars of different ages and chemical compositions across the disk, complicating attempts to read galactic history from present locations alone. A star rich in certain elements may have formed in a chemically different inner region and later traveled outward, carrying its birthplace within its composition even after leaving it far behind. Spiral arms therefore do more than decorate a galaxy. They can help rearrange where stars live, where gas accumulates, and how chemical material becomes distributed over time. Yet the stars do not consciously follow the arms, and the arms do not command them like tracks guiding a train. Both arise from the same changing gravitational system, briefly influencing one another before continuing in new configurations. The spiral you would draw on a galactic map is therefore not a border between permanent communities. It is a meeting place, one that stars enter, transform, and eventually leave, proving that even a cosmic neighborhood can exist without keeping the same residents. The difference between the galactic disk, bulge, and halo. The Milky Way is not one uniform cloud of stars, but a layered system whose regions preserve very different chapters of galactic history. The disk is the broad, rotating plane where most of the galaxy's gas, dust, and younger stars are concentrated. This is the region in which new stars continue to form, because cold gas can gather into dense clouds and collapse under gravity. The disk also contains stars of many ages, but its visible structure is continually renewed by ongoing stellar birth. At the center lies the bulge, a thick, crowded concentration containing mostly older stars, mixed with a smaller population of younger ones. Its stars do not move together in neat circular paths like objects painted onto a spinning wheel. Many follow tilted and elongated orbits that carry them through the dense central region in different directions. The bulge is therefore less like a flat city center and more like a three-dimensional swarm whose structure has been shaped by the galaxy's long evolution. Surrounding both is the stellar halo, a vast and extremely faint population extending far beyond the bright disk. The halo contains scattered ancient stars and globular clusters traveling on wide, often steeply inclined paths. Unlike the disk, it has very little cold gas and almost no active star formation, so it acts more like an archaeological record than a living nursery. Many of its stars may have originated in small galaxies absorbed long ago, while others could belong to the earliest populations formed within the young Milky Way. These regions are not separated by sharp walls. The disk gradually fades, the bulge blends into the inner galaxy, and the halo becomes thinner with distance. Yet their differences in age, motion, shape, and composition allow astronomers to recognize them as distinct components. The Milky Way is therefore not simply a spiral seen from afar, but a collection of overlapping histories. A productive disk still creating stars, a crowded bulge altered by ancient internal changes, and a diffuse halo carrying some of the oldest surviving evidence of how the galaxy came to be. Why the Milky Way is much thinner than it is wide. If the Milky Way contains stars moving in countless directions, why did it become a thin disk instead of a roughly spherical cloud? The answer begins before most of its present stars existed, when the young galaxy contained large amounts of gas moving within a growing gravitational system. Gas behaves differently from stars because clouds can collide, compress, and radiate away energy. When two gas streams meet, their random motions can be reduced, but their overall rotation around the galaxy is much harder to remove. Over time, this causes gas that was initially spread through a thicker volume to settle toward a common rotating plane. Material moving far above or below that plane is pulled back toward it by gravity, while collisions and cooling gradually reduce the motion that would carry it away again. The result is a broad, flattened reservoir from which generations of stars are born. Once a star forms, it no longer collides with surrounding material in the same way, so it largely preserves the motion inherited from its birth cloud. This is why much of the stellar population remains arranged in a disk long after the original gas has changed or dispersed. The disk is still not perfectly flat. Stars move slightly above and below its central plane, creating a thickness that depends on their age and history. Young stars tend to remain close to the thin layer of gas where they formed, while older stars have had more time to be disturbed by massive clouds, spiral structure, and gravitational encounters, giving them larger vertical motions and producing a thicker distribution. The Milky Way's shape is therefore the outcome of two competing tendencies: rotation, spreads matter outward across a wide plane, while gravity pulls it toward the middle and limits how far it wanders vertically. The galaxy did not become thin because something pressed it from above and below. It flattened because moving gas could lose random energy while preserving its shared rotation. What appears from a distance as a graceful, delicate disk is the lasting result of countless collisions, gradual cooling, and gravity repeatedly guiding matter back toward the same invisible plane. How gravity holds the entire galaxy together. The Milky Way does not stay together because its stars are connected, nor because something at the center drags every object around like a rope tied to a wheel. It remains a galaxy because every piece of mass contributes to one shared gravitational field. A star moving through the Milky Way is pulled not only by the central region, but by stars, gas, stellar remnants, and unseen mass distributed across the entire system. The combined effect produces curved paths that keep most objects gravitationally bound. Motion is essential to this balance. If a star suddenly lost its sideways speed, it would begin falling toward denser regions. If it moved too quickly, it could escape. Most stars instead travel at speeds that allow them to continually fall around the galaxy without plunging inward, following orbits that may be nearly circular, stretched, tilted, or slowly changing. The galaxy is therefore held together through constant motion rather than stillness. Gravity also works collectively over immense distances. A single nearby star may briefly influence another, but the smooth pull of the wider Milky Way usually matters more to its long-term path. This is why the galaxy can survive, even though its contents are separated by enormous empty regions. It does not need physical contact to maintain structure. Each object responds to the shape of the gravitational environment surrounding it. The system is also not perfectly stable. Passing galaxies, massive clouds, and internal changes can disturb orbits, sending some stars into new regions or occasionally ejecting them entirely. Yet most disturbances are too small to overcome the binding influence of the whole galaxy. Gravity maintains order without freezing anything in place, allowing the Milky Way to change while remaining recognizable. This may be the most important point. The galaxy is not held together like a building whose parts remain fixed. It is held together like a vast moving pattern where billions of independent objects continually adjust to the presence of all the others. Its unity does not come from rigidity, but from relationship. Every orbit shaped by matter, spread far beyond what any one star could ever see. Why the galactic disk is slightly warped. The Milky Way's disk is not the perfectly flat plate shown in simple diagrams. Near its outer regions, one side bends upward while another curves downward, giving the galaxy a subtle, twisted shape. This warp becomes much stronger far from the central regions, where the disk's gravitational hold is weaker and its material responds more easily to outside disturbances. Astronomers first recognized the distortion by mapping neutral hydrogen gas, which extends beyond much of the easily observed stellar disk and clearly departs from a single flat plane. Later surveys showed that stars participate in the bending as well, proving that the warp is not merely a temporary ripple in gas. Gaia added another important clue by measuring how distant stars move vertically through the galaxy. The data indicate that the warped pattern is not frozen in place. It precesses, slowly changing its orientation, somewhat like a spinning top that begins to wobble. This motion suggests that the outer disk is being continually influenced rather than preserving an ancient bend without change. No single cause has been proven beyond doubt. The gravitational pull of the Large Magellanic Cloud is one strong possibility because this companion is more massive than earlier estimates suggested and is currently producing measurable disturbances throughout the Milky Way. Past encounters with the Sagittarius dwarf galaxy may also have contributed, while a misalignment between the disk and the galaxy's broader mass distribution could apply a persistent twisting force. Fresh gas arriving from the space around the Milky Way might further alter the orientation of the outer disk. These influences may work together, which would explain why the warp is uneven and dynamic rather than a clean, permanent curve. From the solar system, the distortion is difficult to notice because we are too close to the region where its height is still small. Only by comparing distant stars and gas across enormous sections of the sky can astronomers reconstruct the bend. The warp therefore reveals something hidden by the galaxy's familiar symmetry. The Milky Way is not an isolated object resting peacefully in space, but a responsive system still being tugged, disturbed, and reshaped by its surroundings. What looks stable from within may actually be moving through a slow deformation too vast for a human lifetime to witness. How the Milky Way may be larger than its visible edge suggests. A galaxy does not end where its light becomes too faint for your eyes, and this makes the true size of the Milky Way far harder to define than a number printed beside a diagram. The bright stellar disk is commonly described as stretching a little more than 100,000 light-years across, but that measurement refers mainly to the region where stars are concentrated strongly enough to form the recognizable galactic body. Move farther outward and the Milky Way does not meet a wall or stop abruptly. The density of stars gradually declines. Isolated populations continue beyond the prominent disk, and thin reservoirs of gas reach into regions that ordinary photographs barely register. The apparent edge is therefore partly an observational threshold. It marks where the galaxy becomes difficult to detect, not necessarily where it ceases to exist. Astronomers search for its outer limits by counting faint stars, tracing distant gas, studying the motions of remote clusters, and separating genuine Milky Way members from foreground objects and unrelated background galaxies. Each method can produce a different boundary because each is measuring a different component. The main disk may have one practical size, its sparse outer stellar population another, and the region over which the galaxy's gravity influences smaller companions, an even larger one. NASA visualizations place the stellar halo at roughly 300,000 light-years across, about 3 times the width of the bright disk, although even that halo fades gradually rather than ending at a precise surface. This creates an important problem of language. When someone asks how large the Milky Way is, do they mean the diameter of its luminous spiral, the farthest stars plausibly belonging to it, or the entire region gravitationally associated with the galaxy? None of these answers is automatically wrong, but they describe different layers of the same system. The Milky Way shown in familiar illustrations is therefore closer to its brightly illuminated core than to its complete extent. Much of the galaxy's outer territory is so thinly populated that it would appear almost empty from within, yet its stars still carry the motions and history of the larger system. The visible edge is not a border drawn by nature. It is the point where our instruments begin losing the trail, reminding you that the measured size of something can depend as much on how you search as on what is actually there. Why the Milky Way has a thick disk and a thin disk. 2 overlapping populations occupy the Milky Way's disk, and their different motions reveal that the galaxy did not build all of its stars under the same conditions. The thin disk contains most of the stars found near the galactic plane, including many relatively young stars with orbits that remain close to a shared circular direction. It also contains much of the cold material required for continuing star formation, so its population ranges from older suns to stars that have only recently ignited. The thick disk reaches several times farther above and below the plane and is dominated by older stars moving on less orderly paths. These stars possess larger vertical speeds, allowing them to rise far from the midplane before gravity draws them back. They also tend to carry distinctive chemical signatures. Many contain proportionally more elements such as oxygen, magnesium, and silicon relative to iron, suggesting that they formed during an early period when massive stars were enriching the galaxy rapidly before slower sources had produced as much iron. This chemical pattern acts like a clock, separating populations that might otherwise appear similar. The 2 disks are not solid sheets with a clean boundary between them. They overlap, and astronomers classify their stars through combinations of age, composition, and motion. Their existence probably reflects a change in the Milky Way's behavior over time. The early galaxy was likely more turbulent, gas-rich, and frequently disturbed, producing stars with energetic motions that created a thicker distribution. Later, as gas settled into a calmer and more organized layer, new generations formed on flatter, more circular paths, building the thin disk inside the older one. Gravitational disturbances may also have lifted some stars from initially flatter orbits, while slow migration through the galaxy can blur the distinction further. Researchers continue debating how much each process contributed, but observations increasingly show that the thick disk began forming remarkably early and preserves information from the Milky Way's first major phase of growth. The thin disk represents a quieter chapter that followed without completely replacing what came before. You are therefore not living inside a single stellar surface, but within two histories occupying the same space. One shaped by the restless youth of the galaxy, and another formed after part of that turbulence had begun to settle. How the galaxy can contain billions of stars without looking completely bright. If the Milky Way contains an almost unimaginable number of stars, the real mystery is not why the night sky glows, but why darkness survives at all. At first, it seems reasonable to expect every direction to end on the surface of a star, filling the sky with continuous light. Yet stars are not spread through space like paint across a wall. They occupy tiny points within enormous volumes, and the apparent brightness of each one falls rapidly as its light spreads outward. A star twice as far away appears far less bright, and most stars in the galaxy are so distant that their individual light reaches your eyes as only a faint trace or not at all. Even when thousands of unresolved stars blend into a visible glow, they still cover only a small fraction of the sky. The galaxy is also finite. There is not an endless sequence of Milky Way stars extending in every direction. So many lines of sight eventually leave the main stellar population and continue into intergalactic space. The age and life cycle of stars matter as well. Stars are born, shine for limited periods, and eventually fade or collapse, meaning the galaxy has never contained an eternal population illuminating every possible direction. Human vision adds another layer to the illusion. Your eyes adjust to darkness, making bright stars appear sharp against a nearly black background, but they cannot collect weak light as efficiently as a telescope taking a long exposure. A camera can reveal crowded star fields that look almost empty to the naked eye, yet even the deepest photograph does not turn the sky into a solid sheet of white. Darkness remains because light must cross distance, because stars occupy very little of the space around them, and because the Milky Way has boundaries in both size and time. The night sky is therefore not evidence that the galaxy is empty. It is evidence that abundance and brightness are not the same thing. Billions of stars can exist around you while most of their light arrives too weakened, too scattered across distance, or too sparsely distributed to erase the dark spaces between them. How many stars may exist inside the Milky Way? No astronomer has ever counted every star in the Milky Way, and the number usually quoted is not a completed census, but a carefully built estimate. Common estimates place the total somewhere between roughly 100 billion and several hundred billion stars, with the wide range revealing how difficult the task really is. Scientists begin by surveying regions where stars can be measured reliably, then use those samples to infer the populations hidden in more distant or crowded parts of the galaxy. They also estimate the total amount of mass locked inside stars and ask what mixture of stellar masses could produce the light and motion we observe. This sounds straightforward until you remember that one bright star can outshine thousands of faint ones. Measuring total light, therefore, does not immediately reveal the number of stars producing it. Astronomers must model how many stars belong to each mass range, how quickly different types are born, how long they remain visible, and how many have already become dim remnants. Space missions can map enormous numbers of stars with precise positions and motions. But even surveys containing billions of sources still record only a fraction of the galactic population. Crowded regions can blend many stars into a single point. Distant objects may fall below detection limits, and some stellar systems hide 2 or more stars where an observer first sees one. The estimate also depends on what is being counted. Should brown dwarfs, which are too small to sustain ordinary hydrogen fusion, be included? Should dead remnants be placed in the same total as shining stars? Different definitions produce different answers. This is why the Milky Way's population is better understood as a range than as one perfect figure. The uncertainty does not mean scientists know nothing. It means they know enough to recognize where the hidden populations matter. Humanity has mapped the galaxy with extraordinary sophistication, yet we still cannot state exactly how many suns it contains. That gap is quietly instructive. Knowing the shape and behavior of a system does not require knowing every member by name, and sometimes the most honest scientific answer is not a single number, but a boundary around what the evidence allows. Why most stars in the galaxy are smaller than the Sun. The Sun feels ordinary only because it is the one star you know closely, but by galactic standards, it is more massive than most of its neighbors. When astronomers say that most stars are smaller than the Sun, they usually mean lower in mass, because mass determines nearly everything about a star's life. Its internal pressure, temperature, brightness, lifespan, and eventual fate. Stars begin inside collapsing regions of cold gas, but those regions rarely gather material evenly. Turbulence, gravity, magnetic fields, and fragmentation divide large clouds into many smaller cores, and it is much easier for nature to produce numerous modest stars than a few extremely massive ones. Building a large star requires a dense supply of gas to keep falling inward, but the growing star quickly begins resisting its own formation. Intense radiation, strong winds, and high-energy outflows push against the surrounding material, heating or dispersing the very cloud that feeds it. The more massive the star becomes, the more powerful this feedback grows, making continued growth increasingly difficult. Smaller stars do not disrupt their surroundings as violently, so they form more readily and in greater numbers. They also remain visible for much longer. A massive star burns through its nuclear fuel at an extraordinary rate and may survive only a few million years, while a low-mass star can endure for tens of billions or even trillions of years. This creates a powerful accumulation effect. The galaxy continues producing small stars, and almost none of the least massive ones formed since the Milky Way's early history have had time to die. Large stars are born rarely and disappear quickly, while small stars are born often and remain. Their faintness makes them easy to underestimate, because a handful of brilliant stars can dominate a photograph, even while a much larger hidden population surrounds them. The stellar population of the Milky Way is therefore shaped by both birth and survival. Nature prefers to form stars modestly, and time preserves those modest stars far longer. The Sun may appear stable and average from Earth, yet the true average star is cooler, dimmer, and less massive. A reminder that what feels normal from your position may be unusual when viewed across the scale of an entire galaxy. The red dwarfs quietly filling the Milky Way. The galaxy's most common stars are also among the easiest to overlook, glowing so weakly that not a single red dwarf can be seen from Earth with the unaided eye. Red dwarfs are small, cool stars belonging mostly to the faintest part of the main sequence, and their surfaces release far less visible light than the Sun. Their reddish appearance does not mean they resemble dim red lamps in space. To human eyes, a nearby one would still look intensely bright, but compared with hotter stars, a larger share of its energy emerges at red and infrared wavelengths. Because they are so faint, astronomers can detect them only across relatively limited distances, which means the galactic population we notice most easily is not the population that actually dominates. Many red dwarfs have an internal structure very different from the Sun's. In the smallest examples, material circulates through almost the entire star, carrying hydrogen from outer regions toward the core and moving fusion products outward. This continuous mixing allows them to use their fuel with extraordinary efficiency, instead of leaving large amounts of unused hydrogen outside the central burning region. Their interiors therefore change very slowly, and the least massive red dwarfs are expected to remain active for times far longer than the universe has existed so far. None has yet reached the natural end of its life, so astronomers must use models rather than observations to predict how the oldest ones will eventually evolve. Their quiet appearance can also be misleading. Many young red dwarfs possess strong magnetic fields that produce dark star spots, intense ultraviolet radiation, and sudden flares powerful enough to brighten the star dramatically for a short time. This activity matters because planets must orbit close to such a faint star to receive substantial warmth, placing them within reach of repeated bursts that may alter or strip their atmospheres. Yet this does not automatically make every red dwarf planet lifeless. A planet's magnetic field, atmosphere, oceans, chemistry, and the age of its star could all change the outcome, and scientists are still learning how these factors interact. Red dwarfs therefore combine two opposite qualities. They can be stable for almost unimaginable periods while remaining magnetically restless, especially early in their lives. They fill the Milky Way without filling the night sky, shaping the galaxy's true stellar population from below the threshold of ordinary vision. Their existence asks you to reconsider what dominance looks like in nature, because the stars that influence the galaxy most through their numbers are not the brilliant ones that demand attention, but the quiet ones that endure in darkness. Why massive stars are rare but easy to notice. A handful of massive stars can make an entire region of the galaxy look as though it belongs to them, even when they are surrounded by thousands of fainter suns. Their visibility comes from the extreme conditions inside them. Greater mass creates stronger gravitational compression, raising the pressure and temperature of the core and driving energy production at an extraordinary rate. The result is a star that can shine tens of thousands or even hundreds of thousands of times more brightly than the sun, sending much of its energy into blue and ultraviolet light. This brilliance allows astronomers to detect massive stars across distances where ordinary stars would disappear into the background. But the star itself is only part of what becomes visible. Its ultraviolet radiation can tear electrons away from atoms in surrounding gas, creating enormous glowing nebulae that may extend for dozens or hundreds of light years. Its stellar wind can race outward at tremendous speed, carving cavities, piling gas into shells, and compressing nearby clouds. In this way, one massive star can illuminate and reshape a region far larger than its own physical body, leaving a signature that can be studied even when the star is hidden behind dust. These stars also tend to form in groups, so young clusters may contain several brilliant blue stars, whose combined light dominates the surrounding population. This produces a powerful observational bias. When you look at a distant part of the Milky Way, the stars you notice first are not necessarily the most numerous or representative. They are the ones powerful enough to announce themselves across the distance. Astronomers must correct for this bias when estimating stellar populations, because a photograph weighted by brightness can give a false impression of what the galaxy is actually made of. Massive stars also reveal themselves through broad spectral lines, fast winds, violent variability, and chemical material carried away from their surfaces. Some swell into supergiants, some lose their outer layers and expose intensely hot interiors, and some interact with companion stars in ways that dramatically change their evolution. Their rarity is therefore hidden by their influence. They may form only a small fraction of the stellar population, yet they control the appearance, temperature, and chemistry of many star-forming regions. A crowded field of quiet stars can be visually erased by one luminous giant, reminding you that what dominates your attention is not always what dominates reality. Brightness is a form of exaggeration, and the Milky Way often looks different from what it truly contains, because its rarest stars are also its loudest. How stars are born inside the galaxy's coldest clouds. A star begins not in fire, but inside a region so cold and dark that ordinary visible light may reveal almost nothing at all. These stellar nurseries are giant molecular clouds, vast collections of gas and dust, where temperatures can fall to only a few degrees above absolute zero. The cold is essential because warm gas moves rapidly and resists being compressed, while colder material can settle into denser concentrations, where gravity has a better chance of taking control. Most of the cloud is hydrogen, but molecular hydrogen is difficult to observe directly under such conditions. So astronomers often trace the cloud using carbon monoxide emissions and the infrared glow or silhouette of dust. The cloud is not calm or uniform. Turbulence creates knots and filaments. Magnetic fields resist collapse in some regions, and shock waves from nearby stellar activity can squeeze other regions into greater density. Inside the most compressed knots, gravity eventually becomes stronger than the forces supporting the gas. The material begins falling inward, first slowly and then more rapidly, forming a dense central object called a protostar. At this stage, it is not yet a true star because sustained hydrogen fusion has not begun. It shines mainly because falling material releases gravitational energy as it crashes inward and heats up. The collapsing cloud rarely falls directly into the center because even a small amount of rotation becomes amplified as the material contracts. This creates a flattened disk around the protostar, from which gas continues to spiral inward, while dust grains collide, stick together, and begin the long process that may eventually produce planets. At the same time, magnetic fields help launch narrow jets from the poles, carrying material away at high speed. These jets may seem wasteful, but they help the forming star remove excess rotational motion that would otherwise prevent continued growth. The young object remains hidden inside its birth cloud until radiation, winds, and outflows clear away enough material for it to emerge. As the core becomes denser and hotter, atomic nuclei eventually begin fusing and a stable star is born. The process is not perfectly efficient. Much of the original cloud may be dispersed rather than incorporated, and many dense regions never complete the transformation. Star formation is therefore a negotiation between gravity pulling inward and pressure, turbulence, magnetic fields, and feedback pushing back. What finally appears as a simple point of light is the surviving center of a long struggle inside darkness. Every star begins by gathering what was scattered, turning cold material into heat and disorder into a temporary source of light. Why some regions of the Milky Way produce more stars than others? The Milky Way does not create stars at the same pace everywhere. Some regions behave like crowded workshops, while others can hold enormous amounts of gas and remain almost silent. The difference begins with density. A cloud may contain plenty of material, but unless enough of that material is gathered into compact regions, gravity cannot overcome the pressure, turbulence, and magnetic support resisting collapse. This is why the total amount of gas in an area does not tell you how many stars it will produce. Astronomers also look at pressure, temperature, chemical composition, and the movement of gas through the galaxy. In some regions, clouds collide or become compressed by expanding bubbles, stellar winds, or the passage of gas through a spiral pattern. Compression can push a cloud closer to instability, but it does not guarantee that stars will form. Strong turbulence may create dense pockets while tearing others apart, and magnetic fields can slow the collapse by guiding charged particles and helping the cloud resist its own gravity. The inner Milky Way contains large reservoirs of dense gas. Yet even there, the rate of star formation can be unexpectedly low because the environment is turbulent, strongly sheared, and exposed to intense radiation. Farther out in the disk, the gas is more thinly distributed and contains fewer heavy elements and dust grains, which can make cooling and molecule formation less efficient. Between these extremes lie regions where density, cooling, and pressure happen to align more favorably, allowing many stellar nurseries to develop within the same broad area. Timing matters as well. Star formation can occur in bursts, followed by quieter periods after young stars heat, ionize, or disperse the material around them. A region that appears inactive today may still contain the remnants of earlier activity or the raw material for a future episode. The galaxy is therefore not divided into permanently fertile and permanently barren zones. Its productivity changes as gas flows, clouds are disturbed, and previous generations of stars reshape the environment inherited by the next. What determines whether a region shines with newborn stars is not one simple ingredient, but a temporary balance between forces trying to gather matter and forces trying to keep it apart. The Milky Way teaches you that creation does not happen merely because the material exists. It begins only when the surrounding conditions allow scattered matter to stop resisting and finally become something new. How long different stars survive inside the galaxy. A star's lifetime is decided less by how much fuel it owns than by how recklessly it spends it. This is why the largest stars, despite containing far more hydrogen than the Sun, can disappear after only a few million years, while the smallest stars may continue shining for trillions. Greater mass presses a star's core more strongly, raising its temperature and driving fusion at a much faster rate. The star becomes brighter, but that brilliance is purchased by consuming fuel with astonishing speed. Massive blue stars can transform their interiors so rapidly that they live and die before the light from some distant parts of the Milky Way has had time to reach Earth. Sun-like stars follow a slower rhythm. The Sun is expected to spend roughly 10 billion years in its long, stable hydrogen-burning phase, and it is now a little less than halfway through that period. When the hydrogen in its central region becomes depleted, it will not switch off suddenly. Its structure will change, its outer layers will expand, and later stages will continue for a much shorter time before the remaining core becomes a white dwarf. Lower mass stars use fuel even more carefully. Their cores are cooler, their fusion proceeds slowly, and some can mix material through a large fraction of their interiors, allowing them to access hydrogen that a star like the Sun cannot use as efficiently. The least massive true stars are predicted to remain active far longer than the present age of the universe, which means none has yet lived long enough to complete its natural evolution. Stellar lifespan is also affected by companionship. In binary systems, one star may transfer matter to another, stripping away outer layers, increasing the companion's mass, or restarting activity that makes a star appear younger than it really is. Rotation and chemical composition can further alter how material circulates inside a star and how quickly it evolves. There is therefore no single clock that applies to every stellar body. The Milky Way contains stars born recently beside others that began shining near the beginning of galactic history. Yet their survival does not simply reflect age. It reflects how their internal physics manages energy. A bright star may look powerful while standing close to death, and a faint one may seem insignificant while carrying enough fuel to outlast nearly every familiar object in the sky. Longevity in the galaxy belongs not to the stars that burn most dramatically, but to those that have learned through their mass and structure to release their light almost unbearably slowly. How supernova explosions enrich the galaxy. When a supernova tears a star apart, the explosion does more than end one stellar life. It changes the chemical possibilities available to the entire galaxy. The blast throws material outward at enormous speed, carrying atoms that were created or transformed during the star's evolution and during the explosion itself. Core collapse supernovae, produced by massive stars, release large amounts of oxygen, silicon, sulfur, calcium, and other elements into surrounding space. Type Ia supernovae, which involve the destruction of a white dwarf, contribute especially large quantities of iron group material. Yet supernovae are not responsible for every heavy element, and their role must be described carefully. Some elements are built mainly inside aging stars and released through slower winds, while many of the heaviest nuclei are strongly associated with events such as neutron star mergers. Supernovae are important because they distribute a broad chemical mixture and inject it into the interstellar medium with enough energy to move it far from the original star. At first, the ejected material is extremely hot and unevenly mixed. The expanding shockwave sweeps up surrounding gas, forming a growing shell and creating a supernova remnant that may remain visible for thousands of years. Over far longer periods, turbulence, cloud motion, and repeated explosions spread the enriched material through larger regions. The mixing is never perfectly uniform. Two stars born at similar times can contain slightly different chemical patterns, depending on which earlier events contributed to their birth clouds. Astronomers use these patterns almost like fingerprints, comparing ratios of elements to reconstruct where a star may have formed and what kinds of stellar deaths enriched its material. Supernovae also alter the galaxy mechanically. Their shock waves can heat gas and prevent it from collapsing, but they can also compress nearby material strongly enough to help create dense regions. In clusters containing many massive stars, repeated explosions may combine into superbubbles that carve vast cavities and push enriched gas high above the galactic plane. Some of that material can later cool and return, carrying newly formed elements into another generation of clouds. The process is therefore not a simple sequence in which one explosion immediately produces new stars. It is a slow circulation of matter through heat, expansion, mixing, cooling, and reuse. The galaxy becomes chemically richer because it remembers destruction in material form. Every supernova removes one star from the sky, but it also leaves behind new ingredients that future worlds may inherit, turning a violent ending into part of the Milky Way's long education in complexity, the elements created by dying stars. The atoms around you were not all made in the same kind of star, and the final stages of stellar life act less like one universal furnace than a network of specialized workshops. Stars similar to the Sun create helium by fusing hydrogen, but as they age and expand, some begin producing carbon and oxygen in their interiors. During the late red giant and asymptotic giant phases, slow movements of material can carry newly formed carbon toward the surface, where powerful winds release it into space. These aging stars are also important sources of nitrogen and of heavier elements created through slow neutron capture, including strontium, barium, and lead. The word slow does not mean the process is brief by human standards. It means atomic nuclei usually have time to change through radioactive decay before capturing another neutron. More massive stars follow a more extreme path, building layered interiors in which different regions produce different elements. One shell may be dominated by carbon reactions, another by oxygen, and deeper layers can create silicon and other nuclei approaching iron. Iron represents a turning point because combining iron nuclei no longer provides the energy needed to support the star. But even this is not the end of the periodic table's story. Elements heavier than iron require additional processes, especially environments rich in free neutrons. Some are produced during explosive stellar deaths, while a large share of precious metals, such as gold and platinum, appears to come from collisions between neutron stars. This means the phrase "made in stars" is true but incomplete. Different atoms require different stellar masses, internal conditions, lifetimes, and endings. The carbon used by living cells, the calcium strengthening bones, and the copper carrying electricity through modern machines emerged from separate cosmic histories before becoming mixed together. A single handful of Earth may therefore contain material from quiet aging stars, violent explosions, and rare collisions between dead stellar cores. What looks like ordinary matter is really a collection of ancient processes brought into the same place, reminding you that complexity did not come from one event. It was assembled from the specialized work of many stars that never knew one another, yet contributed different pieces to the same future. How star death makes new planets possible. Before stars began dying, the universe contained almost none of the solid material needed to build a world like Earth. Hydrogen and helium could form stars and gas giants, but rocky planets require carbon, oxygen, silicon, magnesium, iron, aluminum, and many other elements that had to be manufactured later. When stars age, they return part of their material to space through winds, expanding outer layers and more violent endings. As this ejected gas cools, some of its atoms combine into microscopic grains of carbon-rich material, silicates, and other minerals. These grains become part of the interstellar medium, where they mix with older gas and with material from many unrelated stellar systems. The process takes time. One dying star does not normally create a finished planet around the next star immediately. Its contribution may travel through space, enter a cloud, be stirred by turbulence, survive radiation and shockwaves, and remain dispersed for millions of years before gravity gathers the cloud into a new stellar nursery. Around a forming star, part of that enriched material settles into a rotating disk. Dust grains collide and sometimes stick, growing from particles smaller than sand into pebbles, larger bodies, and eventually planetary building blocks. The path is not smooth because many collisions destroy objects rather than enlarge them, and young stars can disperse the disk before planets fully form. Yet wherever growth succeeds, the products of earlier stars become landscapes, atmospheres, oceans, and metallic cores. Stellar death also changes how efficiently planets can form. Dust helps clouds cool by radiating energy, allowing some regions to collapse more easily, and it provides surfaces on which simple molecules can assemble. Heavy elements give future planetary systems more chemical possibilities than the earliest universe possessed. This is why planet formation is connected to galactic history. Younger generations of stars are generally born from material that has been processed more thoroughly than the gas available to the first stars. The death of a star is therefore not a direct act of creation, but an act of preparation. It breaks apart an old structure, releases ingredients that were once trapped inside it, and returns them to a shared reservoir where gravity may eventually arrange them into something entirely different. A planet is not the opposite of stellar death. It is one of the forms that recycled stellar matter can take after enough time has passed for destruction to become construction. Why some stars are thrown out of the galaxy at extreme speeds. Star can be born as an ordinary member of the Milky Way and later be accelerated so violently that the entire galaxy may fail to keep it. These rare objects are called hypervelocity stars, and some travel fast enough to escape the Milky Way's gravitational influence and continue into intergalactic space. One of the most powerful ejection mechanisms can occur when a binary star system passes dangerously close to the supermassive black hole at the galactic center. The black hole's gravity can tear the pair apart, capturing one star into a tight orbit while flinging the other outward at an extraordinary speed. This process, often called the Hill's mechanism, converts the binary system's orbital motion into the departing star's velocity. But the galactic center is not the only possible source. In a crowded star cluster, close gravitational encounters among several massive stars can eject the lightest participant. Much as a complicated interaction between moving objects can transfer most of the energy into one body, binary systems can also be disrupted when one member explodes. If the companion suddenly loses the gravitational pull that had held it in orbit, it may continue moving away at its former orbital speed, sometimes receiving an additional push if the explosion is uneven. Astronomers identify high-speed stars by measuring their motion across the sky, their distance, and how quickly they approach or recede from Earth. Missions such as Gaia have made this work far more precise, but determining a star's birthplace remains difficult because small uncertainties grow when its path is traced backward across millions of years. Chemical composition provides another clue. A star resembling the populations near the galactic center may support one origin, while a different elemental pattern may point toward the disk or even another galaxy. Not every fast star will escape. Many remain bound on enormous looping trajectories that carry them far into the outer Milky Way before gravity draws them back. those exceeding the local escape speed may never return, their existence reveals that a galaxy is not a perfectly closed community. Under the right conditions, gravity can act not only as the force that keeps a star in place, but as the mechanism that launches it away. A hypervelocity star carries its light beyond the region that formed it, becoming a solitary record of one extreme encounter and proving that even a sun can lose its galactic home. Why most stellar black holes are almost impossible to find. A stellar black hole can pass through the Milky Way for billions of years without giving astronomers a single obvious sign that it exists. The reason is simple but frustrating. A black hole does not possess a glowing surface, and if no nearby matter is falling toward it, there is almost nothing for a telescope to detect. The dramatic black holes shown in space images are usually active systems surrounded by hot gas, but these represent only a visible minority. Many stellar black holes are likely isolated, while others belong to wide binary systems in which they receive too little material from their companion to produce strong radiation. Even when gas is present, it may form a thin, dim flow rather than a brilliant X-ray source. Astronomers therefore discover most known stellar black holes indirectly. In an X-ray binary, gas pulled from a companion star circles the unseen object, becoming intensely heated before disappearing from view. By measuring the companion's orbit, scientists can estimate the mass of the dark partner and determine whether it is too heavy to be an ordinary star or neutron star. But this method finds only black holes fortunate enough to have a suitable companion and active feeding conditions. Another approach looks for the small wobble of a visible star orbiting an invisible mass, although interpreting such systems requires care because several faint stars can sometimes mimic one heavier object. Gravitational wave observatories have revealed merging black holes that may never have produced detectable light, opening an entirely new census of the hidden population. Yet even this technique catches black holes only during the final moments of rare collisions. Most remain quiet before and after such events. Their darkness creates a severe observational bias. The black holes easiest to study are not necessarily the most common, but simply the ones placed in circumstances that make them visible. Estimates suggest the Milky Way may contain millions of stellar black holes, but the true number depends on how often massive stars formed, how many collapsed successfully, and how many remnants were later ejected or merged. Humanity may therefore share the galaxy with an enormous population of invisible stellar remains that cannot be photographed, counted directly, or even located one by one. They are not hidden behind a curtain. Their hiddenness is their natural state. The deeper lesson is unsettling and useful at the same time. Astronomy is not only the study of what shines, but the art of recognizing when motion, radiation, or silence reveals that something unseen must be there. How colliding stars can briefly outshine entire regions of the galaxy. Some of the brightest stellar events begin not when a star explodes alone, but when two stars lose the ability to remain separate. Most stellar collisions do not begin as random impacts between unrelated suns, because the distances between stars are usually too great. They more often occur in side-binary systems, where two stars have orbited each other for millions or billions of years. As one star expands, it can begin transferring matter to its companion, and in some cases both objects become surrounded by a shared envelope of gas. Friction inside that envelope steals orbital energy, drawing the stars closer until they spiral together. The merger releases an enormous amount of gravitational and thermal energy in a short period, causing the combined object to brighten dramatically. Events known as luminous red novae can become thousands or even millions of times brighter than the sun, producing a red, slowly fading glow as expanding material cools. One well-studied case, V1309 Scorpii, was observed increasing in brightness before erupting, and earlier measurements revealed that its two stars had been orbiting faster and faster as they approached their final merger. The collision did not instantly destroy all the material. Instead, gas was thrown outward, forming shells and dusty structures around the newly merged star. More compact objects can produce even more extreme transients. When two neutron stars collide, the event can create a kilonova, briefly shining with energy from rapidly produced radioactive elements while also sending gravitational waves through space. The exact brightness and color depend on the masses involved, the amount of material ejected, and how quickly that material expands and cools. These events fade because their energy supply is not steady. A normal star can shine for billions of years by continuously releasing nuclear energy, but a merger releases much of its available energy in one violent episode. For days, weeks, or months, the object may dominate the light of its surroundings, then slowly disappear into the background, leaving behind a single altered star, a compact remnant, or in some cases a black hole. This temporary brilliance can fool the eye into thinking the event is larger than the region around it. Yet its true power lies in how quickly stored orbital motion is converted into heat, radiation, and expanding matter. A stellar collision is therefore not merely two objects striking one another. It is the sudden ending of a long gravitational relationship, when an orbit that survived for ages collapses into one brief moment, bright enough to announce itself across the galaxy. The stellar graveyards, hidden throughout the Milky Way. The Milky Way has no single cemetery for dead stars. Its graveyards are scattered everywhere, mixed among living suns and often hidden so well that you could look directly toward one without noticing anything unusual. When stars exhaust the fuel that supports them, they leave behind different remnants depending mainly on their original mass and how they evolved. Stars similar to the Sun shed their outer layers and end as white dwarfs, dense cores roughly the size of Earth that no longer generate energy through ordinary fusion. They begin extremely hot and then cool slowly for billions of years, fading from bright white to dimmer states while preserving information about when their parent stars died. Because their cooling rate can be modeled, populations of white dwarfs act like clocks that help astronomers estimate the ages of star clusters and parts of the galactic disk. More massive stars can leave neutron stars, objects so compressed that matter is packed into conditions impossible to reproduce on Earth. Some reveal themselves as pulsars, sweeping beams of radio waves across space as they rotate, while others remain almost silent if their beams miss Earth or their magnetic activity weakens. Black holes form the darkest endpoints, but they are only one part of this hidden population. Binary systems add further complexity. A white dwarf may steal material from a companion, a neutron star may spin faster after receiving gas, and two remnants may orbit unseen until gravitational radiation gradually brings them together. The galaxy also contains failed and fading systems, old planetary nebula cores, cooled white dwarfs, disrupted binaries, and compact remnants that no longer produce strong signals. These stellar graveyards are not concentrated only in ancient regions. They exist in the disk, the bulge, star clusters, and the halo, reflecting where earlier generations of stars once formed. Their distribution helps scientists reconstruct the Milky Way's past rate of star formation, because every remnant is evidence that a luminous star once occupied that location. Yet the census remains incomplete. Many white dwarfs are too faint, many neutron stars no longer pulse toward us, and many compact remnants have no companion to reveal their gravity. The galaxy you see is therefore only its active surface. Beneath the visible population lies an accumulated history of collapsed cores and cooling remains, growing larger with every passing era. These objects are not empty leftovers. They retain mass, motion, magnetic fields, and sometimes enormous stored energy, continuing to influence nearby systems long after their original stars have vanished. The Milky Way's graveyards teach a quiet truth. Stars do not simply disappear when their light ends. They change form, leaving the galaxy filled with physical memories that can survive far longer than the brilliance that created them. How white dwarfs preserve the history of ancient stars. A white dwarf may look like the quiet end of a star, but inside its fading light is a record of everything that happened before the star died. These compact objects are the exposed cores left behind after stars of low or moderate mass lose their outer layers. And because no ordinary fusion continues inside them, their later evolution becomes unusually simple. They spend immense periods releasing heat stored from their earlier lives. This slow fading allows astronomers to read them as historical evidence. The temperature of a white dwarf reveals how long it has been cooling, while its mass offers clues about the star that originally created it. By combining that cooling age with the estimated lifetime of its parent star, scientists can reconstruct when the star itself was born. In ancient clusters, where many stars formed at roughly the same time, the faintest surviving white dwarfs help place a lower boundary on the cluster's age. Their interiors also preserve information in less obvious ways. As a white dwarf cools, its dense carbon and oxygen interior can begin to crystallize, releasing energy and slightly delaying the fading process. Astronomers must account for this when turning brightness into age, and observations have now revealed populations whose cooling patterns show signs of crystallization. Some white dwarfs pulsate gently, expanding and contracting in regular rhythms. By studying those vibrations, researchers can probe internal layers that no telescope can see directly, learning how much carbon and oxygen lie within and how material is arranged beneath the surface. Their atmospheres tell another story. Heavy elements should sink rapidly under the star's intense gravity. So when metals appear in a white dwarf's spectrum, they often indicate that the star is currently consuming fragments of asteroids or former planets. These polluted atmospheres can reveal the composition of rocky bodies from planetary systems that no longer resemble their original form. A white dwarf therefore preserves several histories at once: the age of its stellar population, the internal chemistry of its parent star, and sometimes the remains of worlds that once orbited nearby. It is not merely a dead ember cooling in isolation. It is an archive compressed to the size of a planet, holding evidence of a star's birth, transformation, and lost surroundings long after the original light has disappeared. The neutron stars spinning inside our galaxy. Somewhere in the Milky Way, a sphere no wider than a city may be rotating hundreds of times every second, carrying more mass than the Sun inside a body of almost unimaginable density. This is a neutron star, created when the core of a sufficiently massive star collapses so violently that electrons and protons are forced into matter dominated by neutrons. The collapse shrinks the core enormously, and the star's original rotation speeds up for the same reason a figure skater spins faster when pulling in their arms. Its magnetic field is compressed as well, becoming powerful enough to guide charged particles along narrow regions above the magnetic poles. If beams of radiation escape from those regions and sweep across Earth as the neutron star rotates, astronomers detect a regular pulse, giving the object the name pulsar. The pulses can be so stable that some neutron stars rival the precision of atomic clocks. Yet their rotation is not perfectly smooth. They gradually lose energy and slow down, but occasionally they experience sudden jumps called glitches, possibly caused by interactions between the rigid outer crust and a strange superfluid hidden inside. These tiny changes offer rare clues about matter under pressures that cannot be recreated in laboratories. Some neutron stars rotate only a few times each second, while millisecond pulsars spin extraordinarily fast. Many of the fastest were probably accelerated later by stealing gas from a companion star, a process that transferred rotational momentum and effectively recycled the pulsar. Their accurate timing has turned them into tools for studying the galaxy. Astronomers use pulsars to test gravity, map the distribution of free electrons between stars, and search for extremely long gravitational waves by comparing the arrival times of pulses from many objects across the sky. Neutron stars may also possess magnetic fields so intense that they are classified as magnetars, capable of producing bursts that can briefly release extraordinary amounts of high-energy radiation. Yet beneath all these observations remains a deeper uncertainty. Scientists still do not know exactly what matter becomes at the center of a neutron star. It may contain unfamiliar states in which the normal identities of particles begin to blur. Each pulse reaching Earth is therefore more than a rotating signal. It is a message from matter pushed almost as far as matter can go without vanishing behind an event horizon, allowing the galaxy to turn one of its smallest objects into one of its most precise and mysterious clocks. The remnants left behind by ancient supernovae. Long after a supernova's brilliant flash has faded from every living memory, its shockwave can continue moving through the Milky Way like an expanding fossil of violence. A supernova remnant is not the dead star itself, but the vast structure created when ejected material crashes into the surrounding interstellar medium. At first, the debris expands almost freely, carrying the chemical and kinetic imprint of the explosion outward at tremendous speed. As it gathers more surrounding gas, the remnant enters a slower stage in which the shock heats material to millions of degrees, producing X-rays that reveal temperatures invisible to human sight. Electrons accelerated along magnetic fields can also generate radio emission, while cooler regions behind the shock may glow in visible light as thin filaments of hydrogen, oxygen, sulfur, and other elements. This is why the same remnant can look completely different depending on the wavelength used to observe it. Some appear as nearly circular shells, others as tangled loops, and still others become distorted when the expanding front encounters dense clouds or uneven gas. The shape can help astronomers reconstruct the environment in which the original star died. By measuring how quickly the outer boundary is growing and comparing the motion of different filaments, researchers can estimate the age and energy of the explosion. Remnants such as the Cygnus loop and Vela have expanded for thousands of years, becoming enormous structures that cover broad areas of the sky despite being too faint to see easily without instruments. Inside some remnants lies a neutron star moving away from the explosion site, occasionally surrounded by a glowing wind nebula produced by energetic particles. In other cases, no compact object is found, either because it is too faint, moving in an unexpected direction, or because the original event left a different remnant. Ancient supernova remains also help scientists investigate the origin of cosmic rays, since their shocks can accelerate charged particles to extreme energies. Though supernova remnants may not explain every cosmic ray observed, eventually, the expanding shell slows, cools, and merges with the surrounding gas until its boundary becomes difficult to distinguish. The explosion has not vanished. It has been diluted into the wider galaxy. These remnants show how the Milky Way remembers catastrophic events without preserving them as fixed monuments. Their history survives in heated gas, bent magnetic fields, accelerated particles, and expanding shells. Evidence that even after the light is gone, space can continue carrying the shape of what happened. The binary star systems hidden across the Milky Way. A point of light that appears to be one star may actually contain two suns locked in a relationship so close that no ordinary telescope can separate them. Binary star systems are found throughout the Milky Way, and in many cases the two stars formed from the same collapsing cloud, beginning their lives together rather than meeting by chance later. Some pairs are separated by vast distances and require centuries or even longer to complete one orbit, while others circle so closely that they finish a revolution in hours. Astronomers uncover these hidden companions in several ways. A telescope may resolve two stars directly if they are far enough apart, but tighter systems reveal themselves through motion. One star may seem to wobble across the sky because an unseen companion is pulling it around a shared center of mass. In spectroscopic binaries, the lines in a star's light shift back and forth as it alternately moves toward and away from Earth. Eclipsing binaries expose themselves when one star repeatedly passes in front of the other, causing the system's brightness to fall in a predictable rhythm. These eclipses allow astronomers to measure stellar sizes and masses with unusual precision, making binary systems some of the best laboratories for testing how stars work. Their shared evolution can become far stranger than the lives of isolated stars. If one star expands, its outer material may cross the gravitational boundary between the pair and begin flowing toward its companion. The receiving star can gain mass, spin faster, and appear younger, while the donor is stripped down to deeper layers that would normally remain hidden. In very close systems, the stars may share a common envelope, spiral inward, or eventually merge into a single object. Some binaries remain stable for billions of years. Others become unstable because each star changes the conditions faced by the other. Their influence extends to planets as well. Worlds can orbit one member of a wide pair, or circle both stars at once, experiencing double sunsets and gravitational patterns unlike anything in the solar system. Binary stars reveal that stellar evolution is often not a solitary process. A star's fate may depend as much on its companion as on its own mass, turning what looks like one quiet light into a continuing exchange of gravity, matter, and time. The enormous clouds floating between the stars. Between the visible stars lie clouds so vast that light can take hundreds of years to cross them. Yet they are so diffuse that a spacecraft could travel through one without meeting anything that feels like a wall. These interstellar clouds contain gas mixed with tiny grains of solid material, and they appear in several forms depending on their temperature, density, chemistry, and exposure to radiation. Some are warm and partly ionized, with atoms separated from their electrons by energetic starlight. Others are cold, neutral regions dominated by atomic hydrogen. The largest molecular complexes contain denser pockets where hydrogen atoms have joined into molecules, and where carbon monoxide, ammonia, water, and more complex compounds can also exist. Their enormous scale can be deceptive because the material inside them is spread extraordinarily thinly by terrestrial standards. Even a cloud dense enough to block distant starlight would still resemble an extreme laboratory vacuum if sampled in a room on Earth. Astronomers map these structures using different signals. Neutral hydrogen produces a distinctive radio emission that passes through obscuring material, while molecules reveal themselves through narrow microwave and radio frequencies. Dust absorbs shorter wavelength light and releases part of that energy in the infrared, making a cold cloud visible through the warmth of grains that may be only slightly above absolute zero. These clouds are never truly motionless. They drift within the galactic disk, stretch under gravity, collide with other gas, and become shaped by pressure from nearby stars. Some are pushed into expanding shells. Others are broken into filaments that can extend across immense distances. Their boundaries are not clean surfaces, but gradual transitions where density, temperature, and ionization change. A large cloud may also contain many different environments at once, with a warm outer layer exposed to radiation and a shielded interior where delicate molecules can survive. Most of its material may remain inactive for long periods, resisting collapse through turbulence, magnetic support, or simple lack of density. Eventually, the cloud may disperse, merge with another, or be reshaped beyond recognition. These enormous formations are therefore not passive fog suspended between stars. They are moving reservoirs that store matter, carry chemistry across the galaxy, and preserve conditions unavailable in the bright regions surrounding stars. Their quiet presence shows that some of the Milky Way's largest structures can remain almost invisible, not because they are empty, but because their substance is spread too gently to announce itself. Why interstellar space is not truly empty. The space between stars looks vacant because human sensors are built for dense environments. But every cubic region of the Milky Way contains particles, radiation, magnetic fields, and moving energy. Interstellar space is filled with a mixture known as the interstellar medium, though it does not exist in one uniform state. In some regions, the gas is cold enough for atoms and molecules to remain together. In others, powerful radiation has heated it into a plasma of free electrons and atomic nuclei. The hottest component can reach millions of degrees, yet it would not instantly burn a traveler because temperature describes the energy of individual particles, not how many of them are present. With so few particles available to transfer that energy, the gas can be extremely hot while remaining extraordinarily thin. Light also occupies this apparent emptiness. Starlight, infrared radiation from dust, radio waves, ultraviolet photons, X-rays, and the faint cosmic microwave background all pass through the galaxy, creating a continuous field of radiation that changes from one region to another. Charged particles called cosmic rays move through interstellar space at nearly the speed of light, carrying far more energy than ordinary gas particles and sometimes striking planetary atmospheres or spacecraft. Magnetic fields thread through the galaxy as well, guiding charged particles and influencing how gas moves, even though those fields are far weaker than a simple household magnet. Tiny dust grains add another hidden layer. They can absorb light, carry frozen molecules on their surfaces, become electrically charged, and scatter radiation in ways that alter what astronomers see. Even gravity reaches across these distances, ensuring that no region is completely disconnected from the surrounding galaxy. The solar system itself moves through this environment, while the sun's outward flowing solar wind creates a protective bubble called the heliosphere. Beyond that boundary, the pressure of interstellar gas, magnetic fields, and energetic particles becomes more direct. This means the space between stars is not a blank stage waiting for objects to pass through it. It is an active environment that affects light, shapes planetary systems, redirects particles, and changes over time. What you call emptiness is really a matter of scale. Compared with Earth's atmosphere, it is almost nothing, but compared with absolute nothingness, it is crowded with structure. The darkness between stars is not an absence of reality. It is a quieter form of reality, too thin for touch, but rich enough to shape everything moving through it. How dust can hide entire regions of the Milky Way. An entire region of the Milky Way can disappear from an ordinary photograph without a single star actually vanishing. The cause is interstellar dust, a population of microscopic solid grains scattered through the galactic disk. These grains are made from carbon-rich material, silicates, metals, and compounds built and recycled through many generations of stars. Each grain is tiny, but across thousands of light years their combined effect becomes enormous. Visible light striking the dust is partly absorbed and partly scattered away from its original path, so distant stars appear dimmer than they truly are. Blue light is scattered more strongly than red light, which also makes hidden stars look redder, an effect astronomers call interstellar reddening. This creates a serious scientific problem. A star may seem faint because it is far away, because it is naturally weak, or because a veil of dust is blocking much of its light. Unless astronomers correct for that veil, they can misjudge the star's distance, brightness, temperature, and even the structure of the region around it. Entire star-forming complexes, sections of spiral arms, and crowded fields can therefore remain missing from visible light maps. The dark lanes crossing the Milky Way are not gaps in the galaxy. They are places where foreground dust has removed so much background light that rich stellar populations become almost invisible. Scientists escape this blindness by changing the kind of light they observe. Infrared radiation passes through many dusty regions more easily than visible light, revealing stars that appear absent in ordinary images. Radio observations can trace gas within and behind the dust, while sub-millimeter instruments detect the cold grains themselves by measuring the faint energy they release. By comparing these wavelengths, astronomers can estimate how much dust lies along a line of sight and reconstruct what the visible sky has concealed. Dust is therefore both an obstacle and a source of information. It hides the galaxy's interior, yet its temperature, composition, and distribution reveal where matter is gathering, where stars have recently lived, and where future activity may occur. What looks like darkness is not simply a failure of light to exist. It is evidence that light has met something on its journey, reminding you that the galaxy you see is shaped not only by what shines, but by everything standing between you and the source. Why dark nebulae look like holes in the night sky. The blackest patches in the night sky are often not the emptiest places, but some of the most heavily filled with cold material. Dark nebulae look like holes because they are seen in silhouette against brighter backgrounds. Behind them may lie dense star fields, glowing hydrogen, or the broad light of the Milky Way, while the nebula in front blocks enough of that background to create a sharply defined dark shape. Human vision interprets the missing light as an opening, much as a doorway appears black when the room beyond is unlit. But the astronomical reality is almost the opposite. The darkness marks the presence of a cloud containing gas and dust, sometimes dense enough to hide thousands of stars. Famous examples such as the Coalsack Nebula and the dark structures within the Great Rift can look like empty wounds across the sky. Yet radio and infrared observations reveal substantial matter inside them. Their appearance also depends on geometry. A similar cloud placed against an empty part of the sky might be nearly impossible to notice because there would be little background light for it to block. A dark nebula becomes visually dramatic only when nature provides its own backlighting. Astronomers confirm that these shapes are real foreground objects by counting how the number of visible stars drops across the cloud, measuring how starlight is reddened near its edges, and detecting molecules and coal dust at wavelengths the eye cannot see. Some dark nebulae are enormous complexes stretching across many light years, while others are compact objects called Bok globules, small rounded clouds that may contain only a few solar masses of material. Their crisp outlines can slowly change as nearby radiation erodes their surfaces, or as internal gravity alters their structure. Not every dark nebula is actively producing stars, and a black appearance alone cannot reveal whether collapse has begun. Some are stable for long periods, some are being disrupted, and some hide young objects deep inside. This is why the visual label hole is so misleading. A true hole would contain less matter than its surroundings, but a dark nebula may be darker precisely because it contains more. The lesson is quietly unsettling. Absence in an image does not always mean absence in reality. Sometimes the place where you see the least is the place where the most has gathered, waiting behind a surface that visible light cannot cross. The cold molecular clouds, where future stars are waiting. Before a star is born, it may spend hundreds of thousands or even millions of years inside a cloud that appears to be doing almost nothing. These cold molecular clouds are not merely storage rooms filled with unused gas. They are delicate environments in which gravity, turbulence, magnetic fields, radiation, and chemistry remain locked in a long contest. Their interiors are cold enough for hydrogen to exist, mainly as molecules, and for atoms such as carbon, oxygen, and nitrogen to join into more complex compounds. Dust grains become coated with thin layers of ice containing water, carbon monoxide, methane, ammonia, and other molecules, creating surfaces where reactions can occur even when the surrounding gas is too cold for many collisions to be effective. Weak cosmic rays penetrate the darkness and provide small amounts of energy, helping drive a slow chemistry that would be impossible in complete isolation. Yet most of the cloud does not immediately turn into stars. Turbulent motion can gather gas into dense filaments while also preventing those filaments from collapsing. Magnetic fields can channel material, support some regions against gravity, and slow the movement of charged particles. External pressure may compress a cloud, while ultraviolet radiation from distant stars can heat and erode its exposed edges. Within this changing environment, astronomers search for starless cores, compact, cold concentrations with no internal source of light. Some of these are temporary knots that will disperse. Others become prestellar cores, meaning gravity has gathered enough material that collapse appears likely, even though no protostar has formed yet. Distinguishing the two requires measurements of density, temperature, internal motion, and magnetic support rather than a simple photograph. The word waiting is therefore only partly metaphorical. Matter may remain close to the threshold of collapse for a very long time, repeatedly compressed and released before one region finally becomes unstable. During that silent interval, the cloud is already preparing the conditions of the future system. Its chemistry influences which molecules and ices may later enter a planetary disk. Its rotation affects how material will be arranged, and its internal structure may decide whether one star, a binary pair, or an entire small cluster eventually forms. The first chapter of a star's life is therefore written before the star exists, in a place with no visible flame and almost no obvious motion. Creation begins not with sudden brightness, but with a long period of balance, where the future remains possible without yet becoming inevitable. How nebulae glow in different colors. A nebula can look crimson in one photograph, turquoise in another, and nearly colorless through a telescope, yet none of those views has to be false. The color depends first on what kind of nebula you are seeing, and then on how its light is recorded. In an emission nebula, nearby hot stars flood surrounding gas with energetic ultraviolet radiation, knocking electrons away from atoms. When those electrons later return to lower energy states, the atoms release light at very specific colors, almost like chemical fingerprints written across the spectrum. Hydrogen often produces a deep red glow, while ionized oxygen can shine blue-green, and sulfur contributes darker red tones. These colors do not blend randomly. They reveal temperature, density, and the amount of energy moving through the gas. Reflection nebulae work differently. Their gas is not glowing strongly on its own. Dust grains scatter the light of nearby stars, and shorter blue wavelengths are scattered more efficiently than red ones, giving many reflection nebulae a cool blue appearance. Planetary nebulae may display several layers because their expanding gas contains different elements and different levels of ionization, while supernova debris can show thin filaments whose colors change from one region to another as shocks heat and excite the material unevenly. But photographs add another layer of interpretation. Human eyes are poor at seeing color in extremely faint light, so a nebula that appears gray through an eyepiece may reveal vivid hues in a long exposure. Astronomers also use narrow filters that isolate particular wavelengths, assigning visible colors to signals that might otherwise be difficult to compare. In some images, the colors are close to what a sensitive human eye might perceive. In others, they are deliberately mapped to highlight chemical structure, temperature, or motion. This does not make the image deceptive. It makes the invisible relationships easier to read. A telescope photograph is often less like a casual snapshot and more like a scientific map, where color carries information rather than decoration. Once you understand this, a glowing nebula stops being merely beautiful. Its red edges, green interior, or blue veil become evidence of which atoms are present, how strongly they are being energized, and what kind of stars are shaping the region. The colors are not painted onto the cloud by nature for your benefit. They are the visible result of matter exchanging energy, and when you learn how to read them, the nebula becomes a message written in light. The hot gas surrounding the galactic disk, far above and below the Milky Way's bright disk, lies an atmosphere so hot that ordinary atoms are stripped of many of their electrons, yet the gas is so thin that you could pass through it without feeling heat in any familiar sense. Astronomers often call this extended material the galactic corona, or the hot phase of the circumgalactic medium. It reaches far beyond the regions crowded with stars and may contain a significant fraction of the normal matter associated with the Milky Way. This is important because inventories of stars, cold gas and dust do not account for all the ordinary matter expected from measurements of the early universe. Some of that missing material may be hiding in this vast diffuse reservoir. The gas is heated to hundreds of thousands or millions of degrees, probably through a combination of processes: energetic outflows from the disk, repeated stellar activity, matter falling into the galaxy's gravitational field, and collisions between gas moving at different speeds. At such temperatures, it radiates mainly in ultraviolet and X-ray wavelengths rather than visible light. Astronomers detect it indirectly by observing how it absorbs particular wavelengths from bright sources located behind it. or by measuring its faint X-ray glow across large areas of the sky. Highly ionized oxygen is especially useful because it leaves recognizable marks in a spectrum, allowing scientists to estimate the gas's temperature, motion, and amount. This corona is not simply a static shell. It appears to participate in a slow circulation between the galaxy and the space around it. Gas driven out of the disk can rise, cool, mix with surrounding material, and later return in a process sometimes described as a galactic fountain. At the same time, fresh material from outside the Milky Way may enter the halo, lose energy, and eventually contribute to the galaxy's future supply of gas. The boundary between inside and outside the galaxy is therefore much less clear than a photograph suggests. The bright disk is only one layer within a much larger ecosystem that exchanges matter over immense periods. The hot corona may regulate how quickly the Milky Way can form stars, how efficiently it retains material, and how strongly it interacts with nearby satellite galaxies. Yet it remains difficult to map because it is both widespread and faint. And observations made from inside the Milky Way must separate its signal from local hot gas closer to the solar system. The result is a strange scientific situation. The galaxy may be surrounded by an enormous reservoir that influences its evolution, while remaining almost completely absent from ordinary images. What appears to be empty space above the disk may actually be one of the Milky Way's largest and most important components, reminding you that a galaxy's visible body can be only the cool, luminous center of a much hotter and wider environment. How shock waves travel through interstellar space. A shock wave in interstellar space does not travel like a sound through air. It moves as a sudden reorganization of particles, magnetic fields, and energy across a medium so thin that direct collisions between atoms may be rare. On Earth, a shock forms when matter is compressed faster than information can move through it, creating an abrupt jump in pressure, density, and temperature. The same basic idea applies in the Milky Way, but the interstellar medium is often a plasma, meaning many particles carry electric charge and respond strongly to magnetic fields. Because ordinary particle-to-particle collisions are too infrequent to build the shock front, interstellar shocks are often called collisionless. They are maintained instead by electromagnetic interactions. Charged particles approaching the front encounter disturb magnetic fields, are scattered, reflected, and redirected, and collectively produce a narrow boundary where the gas changes state. Behind that boundary, material can be heated to extreme temperatures, magnetic fields can become compressed and tangled, and particles can gain enormous energies. This is one reason shock waves are considered important accelerators of cosmic rays. Some particles cross the front repeatedly, bouncing between magnetic disturbances on either side and gaining energy with each passage, rather than receiving one single push. Shocks can be launched by several events: fast winds from young stars, explosive stellar outflows, expanding bubbles, jets, or clouds moving rapidly into one another. Their behavior depends on what they encounter. In thin, hot gas, a shock may remain broad and energetic for a long time. When it enters a dense cloud, it can slow, compress the material, and radiate away energy more efficiently. In some cases, that compression may help create dense structures. In others, it can tear a cloud apart, stir turbulence, or strip material from its surface. The same shock can therefore produce very different consequences across neighboring regions. Astronomers trace these fronts through X-rays from extremely hot gas, radio emission from fast electrons spiraling through magnetic fields, and narrow visible filaments where cooling atoms release light. Spectral measurements reveal how rapidly the gas is moving and whether electrons and heavier particles have reached the same temperature behind the front. These details matter because a shock is not merely a moving wall. It is a conversion process, turning organized motion into heat, radiation, magnetic disorder, and high-energy particles. Over time, the front weakens as it spreads its energy through a larger volume, but the changes it leaves behind can persist. Heated cavities, compressed shells, altered chemistry, and turbulence that continues long after the original event has faded. Shockwaves show that even a nearly empty medium can carry force across enormous distances. Interstellar space may be sparse, but it is not fragile. Given enough speed and energy, its thin particles can organize into a front powerful enough to reshape clouds, accelerate matter, and rewrite the conditions of regions light years away. The magnetic field threading through the Milky Way. The Milky Way is threaded by an invisible structure that can guide particles across thousands of light years, influence the movement of gas, and bend without ever becoming visible as a physical wire. This galactic magnetic field is extremely weak compared with the field of an ordinary refrigerator magnet, but its influence becomes important because it fills such an immense volume and acts continuously on electrically charged matter. It is not one smooth loop wrapped neatly around the galaxy. Observations reveal an ordered component broadly aligned with the galactic disk, smaller turbulent fields twisted by moving gas, and structures extending into the halo above and below the plane. Astronomers reconstruct this hidden geometry by watching how magnetism changes light. Elongated dust grains tend to align partly with the surrounding field, causing their thermal emission to become polarized in preferred directions. ESA's Planck satellite mapped this polarized glow across the entire sky, revealing long strands and tangled patterns that trace the projected orientation of the field. Radio observations provide another view. When polarized radio waves pass through ionized gas, the magnetic field rotates the direction of their polarization through a process called Faraday rotation. Pulsars are especially useful because their distances can be estimated, allowing astronomers to compare how much rotation accumulates along different sections of the line of sight. Fast-spinning electrons also produce polarized synchrotron radiation as they curve through magnetic fields, exposing field components that other methods cannot measure as clearly. By combining these clues, researchers can build models of a structure that no instrument can photograph directly, though important uncertainties remain, including exactly how often the large-scale field reverses direction across the disk. The field may be sustained by a galactic dynamo, the rotation of the Milky Way, turbulent motion in electrically conducting gas, and repeated circulation can stretch and amplify weaker magnetic seeds over immense periods. Once established, the field becomes part of the galaxy's active machinery. It can resist or redirect moving gas, shape filaments, influence how energy travels through the interstellar medium, and help connect regions that appear separate in visible light. Yet it does not control everything like an invisible skeleton. Gravity, turbulence, pressure, radiation, and magnetism compete, with their relative importance changing from place to place. The field is better understood as a flexible network responding to the galaxy while also helping shape it. This makes the Milky Way more than a collection of stars moving through empty darkness. It is a magnetized environment in which motion leaves patterns across space, and where something far too weak for your hand to feel can become powerful simply because it never stops acting. How cosmic rays move across the galaxy. A cosmic ray reaching Earth may have crossed the same region of the Milky Way many times, even though the particle itself has been moving at nearly the speed of light. Cosmic rays are mostly protons and atomic nuclei stripped of their electrons, with a smaller population of electrons and other particles, and their electrical charge prevents them from traveling through the galaxy in simple straight lines. As they move, the Milky Way's magnetic field bends their paths into broad spirals. Irregularities and turbulence in that field repeatedly scatter them, changing their direction so often that their overall journey begins to resemble a random walk. A particle may race enormous distances in a short time along its immediate path, yet make slow progress away from the region it came from because its direction keeps being rearranged. This process is known as diffusion, and it helps explain why cosmic rays arrive at Earth from almost every direction rather than pointing clearly back toward individual sources. Their wandering also means that the distance they actually travel can be far greater than the straight line separation between their origin and the solar system. Scientists estimate how long these particles remain in the galaxy by studying rare secondary nuclei. Elements such as carbon and oxygen can strike atoms in interstellar gas and break into lighter fragments, including boron. Because comparatively little boron is expected to be produced directly at the main cosmic ray sources, the amount found among arriving particles reveals how much matter the cosmic rays crossed during their journey. Radioactive forms of some elements provide an additional clock, suggesting that many galactic cosmic rays wander for millions of years before escaping. Their routes depend strongly on energy. Lower energy particles are bent and scattered more effectively, while the most energetic particles follow wider curves and can leave the galaxy more easily. At extreme energies, some may travel almost straight enough for their arrival directions to preserve clues about where they came from. But these particles are rare. Cosmic rays also reveal their paths indirectly when they collide with interstellar gas and produce gamma rays, allowing astronomers to map regions where energetic particles and matter overlap. Near the solar system, the Sun adds one final filter. Its expanding solar wind and magnetic field form the heliosphere, which blocks or redirects part of the lower energy galactic cosmic ray population, with the amount entering the inner solar system changing during the solar cycle. By the time one particle reaches Earth's atmosphere, its original direction may have been erased by millions of years of magnetic wandering. It arrives not as a clean arrow from a distant event, but as a survivor of a galactic maze. Cosmic rays therefore teach you that speed does not always produce a direct journey. A particle can move almost as fast as nature allows, while spending most of its existence being turned, scattered, delayed, and stripped of the story of where it began. Why the Sun lives between two major spiral arms. The Sun's position between two major spiral arms may look like a carefully chosen shelter, but there is no evidence that the galaxy deliberately placed it there, or that it has remained in the same type of neighborhood throughout its life. Today, the solar system lies within the local arm, also called the Orion Arm or Orion Spur, positioned between the larger Sagittarius Carina and Perseus arms. The phrase "between the arms" can be misleading, because the spaces separating major arms are not empty, and the local arm is not merely a few isolated stars floating in a blank gap. Measurements of distant star-forming regions indicate that it is a long and active structure, perhaps a branch or substantial arm segment, whose precise connection to the wider spiral design is still being studied. The Sun's location is therefore determined partly by how astronomers classify a galaxy whose boundaries are broad, irregular, and constantly changing. There is also no simple answer to why the Sun occupies this position now. The Sun formed about 4.5 billion years ago, and during that time the Milky Way's spiral patterns, central bar, gas distribution, and stellar orbits have all evolved. Stars preserve motion, not street addresses. Their paths can be gradually altered by repeated gravitational interactions with spiral structure and the galactic bar, allowing some to shift closer to or farther from the center while maintaining relatively calm orbits. This process makes it extremely difficult to reconstruct the Sun's exact birthplace. Different studies using stellar chemistry, galactic models, and orbital histories have produced different estimates, with some suggesting the Sun formed near its present galactic distance, and others favoring an origin significantly closer to the center. The disagreement is important because it prevents a comforting story from being mistaken for established fact. The Sun may have formed inside a stronger arm, near the early version of the local arm, or in a region whose ancient structure no longer exists. Its present interarm position is only a snapshot taken after billions of years of galactic change. Astronomers have sometimes proposed that living between major arms could reduce exposure to nearby massive star activity or dense molecular environments, potentially making the region calmer for long-term biological evolution. But such galactic habitability arguments remain uncertain because spiral arms are not permanent danger zones. Stars pass through changing environments, and Earth's survival depends on many local conditions that cannot be reduced to one galactic address. The most scientifically honest answer is therefore less dramatic, but more revealing. The Sun lives here because its formation and subsequent orbit placed it here within an evolving disk. Not because this region was prepared in advance. Your location in the Milky Way may have influenced the history of the solar system, but it is neither fixed nor fully understood. Home, on a galactic scale, is not a permanent coordinate. It is the place a moving star happens to occupy while the map around it is being redrawn. How far the solar system is from the galactic center. The center of the Milky Way is so distant that the light reaching Earth from that direction began its journey before modern humans had created cities, farms, or written language. The solar system lies approximately 26,000 light-years from the galactic center, although astronomers continue refining the figure and usually express it as a carefully measured range rather than a perfectly fixed address. This distance is one of the most important numbers in galactic astronomy because it affects nearly every attempt to calculate the Milky Way's dimensions, rotation, mass, and internal structure. Measuring it is not as simple as aiming a ruler toward the middle of the galaxy. The center is obscured at visible wavelengths, and there is no bright physical signpost that marks an exact geometric point. Astronomers instead define the center through the concentration of mass and the motions of objects around the compact source, Sagittarius A*. Several independent methods are then used to determine how far away that region is. One approach follows the orbits of stars near the center and compares their motion across the sky with their speed toward or away from Earth. Because these are two different views of the same orbit, researchers can reconstruct the true scale of the system and obtain a geometric distance rather than relying only on assumptions about brightness. Radio astronomers add another method by observing natural mazes associated with star-forming regions across the Milky Way. These intense radio signals can be measured with networks of telescopes separated by entire continents, allowing scientists to detect tiny shifts in apparent position and map the galaxy from within. Variable stars and red clump stars provide additional distance clues, though dust, crowding, and differences in stellar composition must be corrected carefully. The remarkable result is that techniques based on different objects and different wavelengths broadly converge near the same distance. Yet even a measurement of 26,000 light-years can remain emotionally abstract. If you could travel at the speed of light, which no spacecraft with mass can do, the journey would still last about 26,000 years. A message transmitted today would reach the central region only after the entire span of recorded human history had passed several times over. The solar system may appear on diagrams as a small dot connected to the center by a short line, but that line represents an expanse containing vast numbers of stars and environments that humanity has never visited. Knowing our distance from the center gives us a galactic coordinate, but it also reveals how little of the space between here and there has ever entered direct human experience. We have measured our place with extraordinary precision, while remaining physically confined to an almost invisible patch at one end of the measurement. Why our position in the galaxy may be helpful for life. Life on Earth may have benefited from living in a region of the Milky Way where the ingredients for rocky planets are available, without the surrounding environment being as intense as it is in some other galactic locations. This idea is often discussed through the concept of a galactic habitable zone, but it must be treated as a scientific hypothesis rather than a sharply defined ring where life is allowed to exist. Different parts of the Milky Way offer different advantages and risks. Closer to the center, generations of stars have had more time to enrich the surrounding gas with elements needed to build rocky planets, complex chemistry, and metallic planetary cores. But the inner galaxy also contains a much greater density of stars, more frequent energetic events, stronger radiation fields, and a higher probability of close gravitational encounters. None of these conditions automatically sterilizes every planet, yet together they may make long periods of environmental stability more difficult in certain locations. Far into the outer galaxy, the stellar surroundings become quieter and more widely separated. But the material from which stars form generally contains fewer heavy elements. That could reduce the likelihood of building large rocky planets or chemically rich systems. Although planets have been discovered around stars with a wide range of compositions, showing that the relationship is not simple. The Sun occupies an intermediate galactic distance where enough earlier stellar generations had enriched its birth material, while the present surrounding stellar density is modest compared with the central regions. This balance may have helped Earth retain a relatively stable environment over billions of years, giving biological evolution time to move from simple organisms toward complex ecosystems. Yet the word may is essential. We have only one known inhabited planet, so we cannot compare Earth with a confirmed population of living worlds at other galactic distances. Models of galactic habitability produce different results depending on how they estimate planet formation, supernova danger, gamma-ray bursts, chemical enrichment, and the resilience of life. Some studies suggest broad middle regions are statistically favorable, while others find that large parts of the galaxy could host habitable planets, and that the inner Milky Way's greater number of stars might compensate for its higher hazards. The galaxy also changes over time. A region poor in heavy elements early in cosmic history can become richer later, while the rate of dangerous stellar events gradually rises and falls. Habitability is therefore not simply a place on a map. It is a relationship between location, era, planetary protection, atmosphere, geology, and biological adaptability. Our position may have improved the odds, but it did not guarantee the outcome. Earth's existence should not tempt you into believing that the solar system occupies the only safe address in the galaxy. It may instead show that life can emerge when many favorable conditions overlap for long enough, leaving the deeper question unresolved. Are we living in an unusually fortunate region, or merely in the first inhabited region we have learned how to recognize? How fast the Sun moves around the Milky Way. At this moment, the Sun is carrying Earth through the galaxy faster than any human-built spacecraft has ever traveled. Yet a glass of water on your desk remains perfectly still. The solar system moves around the center of the Milky Way at roughly 220 to 230 kilometers per second in commonly used estimates, equivalent to around 800,000 kilometers per hour. The exact figure depends on what astronomers mean by the Sun's speed and which model of the galaxy they adopt. There is an idealized circular speed for an object following the average motion of material at the Sun's galactic distance, and there is the Sun's actual velocity, which includes smaller movements relative to nearby stars. The Sun does not travel on a perfectly smooth circular track drawn through an unchanging gravitational field. It moves slightly inward and outward, rises and falls relative to the galactic plane, and responds to the uneven distribution of mass across the Milky Way. This makes its velocity a three-dimensional motion rather than one simple number. Scientists measure it by observing the movement of many stars, tracing radio sources across the galaxy, and studying the apparent motion of Sagittarius A against extremely distant background objects. Because the central radio source is expected to remain close to the Milky Way's gravitational center, most of its observed movement across our sky is actually a reflection of the solar system traveling around it. Gaia has added another form of evidence by detecting the tiny change in the direction of distant objects caused by the solar system's galactic acceleration. This effect is extraordinarily subtle, but across a catalogue of many sources, it reveals that our trajectory is continually being curved toward the center. Speed alone does not make you feel motion because you share it with Earth, the Sun, and nearly everything in the surrounding solar system. Your body notices local acceleration, vibration, and changing pressure, not the enormous steady velocity inherited from a galactic orbit. Even so, the number can be made more tangible. In 1 second, the Sun travels far enough along its galactic path to cross the distance between many large cities. During an ordinary night's sleep, it carries you millions of kilometers farther through the Milky Way, although the stars appear almost unchanged because the galactic scale is vastly greater. The Sun is not sitting inside the galaxy while the Milky Way rotates around it. It is one moving member of the system, continuously falling through the galaxy's gravitational field, while its sideways motion prevents it from plunging toward the center. What you call standing still is therefore a local experience created inside a much larger movement. You wake each morning in almost the same room, but never at exactly the same place in the galaxy. Why the solar system does not travel in a perfect circle. The Sun's path around the Milky Way is not a flawless circle drawn through space, but a slowly changing curve shaped by a galaxy that is neither perfectly smooth nor perfectly symmetrical. A planet such as Earth travels mainly under the influence of one dominant central object, so its orbit can be approximated as a stable ellipse. The Sun's galactic motion is far more complicated because the Milky Way's mass is spread across its disk, central bar, gas clouds, stellar populations, and extended halo. Instead of responding to one concentrated source, the solar system moves through a broad gravitational landscape whose strength changes from place to place. The Sun carries enough sideways motion to remain in orbit, but its present speed and direction do not place it on one exact circular track. It drifts slightly inward and outward around an average galactic distance, producing a gentle radial oscillation sometimes compared with a small wave riding on a much larger orbit. Seen over immense periods, its route would resemble a rotating rosette rather than a closed ring, because the point of closest approach to the center does not return to precisely the same direction after every circuit. The central bar and spiral patterns can add further disturbances by exchanging small amounts of orbital energy with passing stars. Encounters with massive molecular clouds may also alter a star's motion, while the gravitational influence of satellite galaxies can introduce broader changes into the disk. None of these effects needs to be dramatic during a human lifetime. A tiny alteration repeated across millions of years can move a star into a noticeably different galactic neighborhood. The Sun also has its own peculiar motion relative to nearby stars, meaning it does not travel at exactly the average speed or direction of the surrounding population. Astronomers reconstruct this complex path by measuring the motions of nearby stars, mapping the galaxy's gravitational field, and running models backward and forward in time. But uncertainty grows rapidly the farther they try to trace the orbit, because small errors and unrecorded gravitational encounters accumulate. This is why the exact birthplace of the Sun cannot simply be recovered by reversing its present motion like a film. Its galactic journey has been adjusted repeatedly by a changing environment. The solar system does not follow a perfect circle, because the Milky Way is not a perfect machine. It is an evolving system filled with moving concentrations of mass, and the Sun's orbit carries the memory of every imbalance it has passed. Your galactic address is therefore not written on a fixed ring. It shifts slowly as the entire solar system negotiates its path through a landscape that never becomes completely still. How the Sun moves up and down through the galactic disk. While the Sun travels around the Milky Way, it is also performing a second, quieter journey, rising above the galactic midplane and later being drawn back through it. The disk is not an infinitely thin surface, but a broad layer containing stars, gas, and other mass spread above and below a central plane. When the Sun moves away from that plane, the combined gravity of the disk pulls it back toward the region where matter is most concentrated. But the Sun does not stop when it reaches the middle. Its accumulated motion carries it through to the opposite side, where gravity gradually slows the vertical movement, reverses it, and begins another return. This creates an oscillation somewhat like a pendulum passing through its lowest point, although the galactic version is less regular because the Milky Way's mass distribution is uneven and changes over time. The solar system is currently believed to sit several dozen light-years above the disk's central plane, though the exact figure depends on how astronomers define a midplane that is itself slightly warped and disturbed. Measurements of the Sun's motion relative to nearby stars suggest that it continues to participate in this vertical cycle rather than remaining at a fixed height. Models commonly estimate that a complete rise and fall journey takes several tens of millions of years, often somewhere around 60 to 90 million years. So the solar system may cross the midplane roughly twice during each full oscillation. These passages are not like crossing a solid boundary. There is no visible line, shock, or sudden change that would announce the moment. The density of surrounding stars and interstellar material increases gradually toward the middle and decreases gradually away from it. Some researchers have explored whether repeated plane crossings could affect comets or coincide with changes in Earth's geological record, but proposed links to mass extinctions remain uncertain and have not been established as a reliable pattern. The galaxy contains too many interacting cycles, and Earth's history is too complex for a simple claim that each crossing causes catastrophe. The scientifically valuable lesson is subtler. The solar system's galactic movement has a vertical rhythm that operates far beyond human timescales. The Sun was born with a small motion away from the midplane, and the disk's gravity has been guiding it back and forth ever since. You do not merely orbit the galaxy in one flat track. You are carried through different heights of its stellar environment, repeatedly leaving the densest plane and returning to it without any generation on Earth feeling the crossing. The Milky Way's floor is not a surface beneath you, but an invisible gravitational center that the Sun can pass through endlessly without ever coming to rest. How scientists discovered the black hole at the galactic center. The black hole at the center of the Milky Way was discovered without anyone seeing the black hole itself, through a chain of clues gathered across nearly a century. The story began in the early 1930s, when radio engineer Carl Jansky was investigating interference in long-distance communications and found a persistent radio signal that rose and fell each day with the stars rather than with the Sun. He traced it toward the constellation Sagittarius, revealing that the center of our galaxy was a powerful source of radio emission, even though ordinary telescopes saw mainly obscuring darkness in that direction. Later radio surveys resolved a complex central region called Sagittarius A, but the decisive step came in 1974, when Bruce Ballack and Robert Brown used radio interferometry to identify an extraordinarily compact source within it. The object became known as Sagittarius A, with the asterisk added to mark its unusual and exciting nature. Its small apparent size and strong radio emission suggested that something extreme was concentrated there, but a compact radio source alone did not prove the existence of a supermassive black hole. Astronomers needed to measure the gravity of the unseen object. Beginning in the 1990s, teams using increasingly powerful infrared telescopes started tracking stars hidden behind the dust near the galactic center. Infrared light allowed them to see through much of the obscuring material, while adaptive optics corrected the blurring caused by Earth's atmosphere. Year after year, the stars shifted position. Some moved so rapidly and followed such tight curved paths that the central mass could not be explained by an ordinary cluster of faint stars. Decades of observations showed that about 4 million times the mass of the Sun was confined within an extraordinarily small region. Alternative explanations, such as a dense collection of neutron stars or other dark objects, became increasingly implausible because such a cluster would collide, evaporate, or collapse on relatively short astronomical timescales. The orbital evidence pointed overwhelmingly toward a single supermassive black hole. This work earned Reinhard Genzel and Andrea Ghez part of the 2020 Nobel Prize in Physics, recognizing the long observational effort that transformed an invisible radio source into one of the best confirmed black holes known. Then, in 2022, the Event Horizon Telescope released an image of glowing material surrounding the dark central region of Sagittarius A, produced by combining radio observatories across Earth into a planet-sized virtual telescope. The image did not show a solid black object, but a bright ring shaped by hot plasma and extreme gravity around a central shadow, consistent with the mass already measured from stellar motion. The discovery was therefore not one dramatic moment or one perfect photograph. It was a gradual argument built from radio noise, precise positions, infrared orbits, gravitational theory, and finally, horizon-scale imaging. Scientists found the black hole by watching everything around it behave as though an enormous invisible object had no other possible identity. Its darkness concealed its appearance, but gravity made secrecy impossible. What the galactic center looks like in infrared light. Point an ordinary telescope toward the center of the Milky Way and much of the scene disappears, but switch to infrared light and the darkness opens into one of the most crowded landscapes in the galaxy. Infrared telescopes do not reveal a simple glowing core with Sagittarius A sitting visibly in the middle. Instead, they show layers of stars, warm clouds, curved streams of gas, and compact sources packed so closely together that separating one object from another becomes a technical challenge. Near-infrared observations are especially useful for identifying individual stars because these wavelengths pass through much of the intervening material and can be recorded with instruments capable of very fine detail. Longer infrared wavelengths reveal cooler dust and heated structures that are less obvious in starlight alone. In many images, the central region appears filled with brilliant points against a diffuse background, while glowing arcs trace gas moving through the inner few light years. One prominent feature is the so-called mini-spiral, a set of ionized gas streams that resembles a small spiral pattern, even though it is not a miniature galaxy. The streams are shaped by gravity, stellar winds, magnetic fields, and the motion of material through the central environment. Their glow comes from gas energized by nearby hot stars, and their changing shapes help astronomers study how matter circulates around the center, without assuming that all of it is falling directly into the black hole. Infrared instruments also reveal stars at different evolutionary stages. Hot young stars, swollen red giants, compact sources surrounded by dust, and objects whose brightness changes as they move or interact with their surroundings. The colors in published infrared images often require careful interpretation. Some are close to natural infrared brightness translated into visible colors, while others assign different colors to different wavelength bands, so temperature and composition become easier to compare. A blue-looking source may represent hotter emission, while redder regions may trace cooler dust. But the exact meaning depends on how the image was processed. Time adds another dimension. Repeated infrared observations show stars shifting, gas structures evolving, and sudden flares appearing near Sagittarius A, turning the galactic center from a static photograph into a monitored environment. What looks from Earth like one dark direction in the sky becomes, in infrared, a complex city of light where different kinds of matter reveal themselves at different temperatures. The transformation is not caused by the center changing when we observe it. It happens because human vision samples only a narrow part of the electromagnetic spectrum. Infrared light does not create the hidden scene. It simply allows you to notice that the darkness was crowded all along. The dense swarm of stars surrounding the central black hole. Around the Milky Way's central black hole lies a stellar population so tightly packed that the night sky from within it would bear almost no resemblance to the calm darkness seen from Earth. This population is known as the nuclear star cluster, a roughly spherical concentration containing millions of stars within a comparatively small region around Sagittarius A. Its density rises dramatically toward the center, bringing stars far closer together than in the Sun's neighborhood. Yet even there, direct collisions between ordinary stars remain less common than the crowded appearance might suggest, because stars are physically tiny compared with the spaces separating them. What changes most is the frequency and strength of gravitational encounters. Passing stars can disturb one another's orbits, exchange energy, break apart binary systems, or push compact objects toward the center over long periods. The cluster contains several generations of stars rather than one population born at the same time. Many are ancient, carrying chemical evidence of the galaxy's early history, while others are unexpectedly young. This creates a famous puzzle. Forming stars near a supermassive black hole should be difficult because strong tidal forces can tear ordinary gas clouds apart before they collapse. Scientists have proposed that exceptionally dense disks of gas may once have formed around the center and fragmented into stars, allowing a young population to appear under conditions that would destroy less compact clouds. Another possibility is that some stars formed farther away and later migrated inward, although this is difficult to accomplish quickly enough for the youngest examples. The central cluster also appears to contain fewer bright red giant stars in its innermost region than simple models predict. Some may have had their expanded outer layers stripped during encounters, while others may be hidden, transformed, or less numerous because of the cluster's unusual history. Beneath the visible population, astronomers expect many white dwarfs, neutron stars, and stellar black holes to have accumulated through a process in which heavier objects gradually lose orbital energy and sink inward. Detecting this dark population is difficult, but occasional X-ray sources, unusual binaries, and gravitational effects may provide clues. The nuclear cluster is therefore not merely a bright crowd surrounding a central object. It is a long-running gravitational experiment where age, mass, motion, and proximity reshape stellar lives. Every star enters the swarm with its own history, yet the environment gradually alters what futures remain possible. Near Sagittarius A star is not isolated enough to evolve, as though the rest of the galaxy were distant. It belongs to a system where the surrounding population becomes part of its fate, showing that even stars can live differently when solitude is removed. Why the center of the Milky Way is filled with dust and radiation. The center of the Milky Way is filled with dust and radiation because matter has been processed, concentrated, destroyed, and recycled there for billions of years. Gas moving through the inner galaxy can lose energy through collisions and gravitational interactions, allowing part of it to settle into dense clouds and ring-like structures near the central regions. Within those environments, stars form, evolve, and return material to space through winds, eruptions, and explosive deaths. Dust grains grow from elements released by earlier stars, including carbon-rich compounds and silicate minerals, then become mixed into surrounding gas. These grains are not permanent. Powerful radiation can heat them, shockwaves can shatter them into smaller pieces, and extreme temperatures can destroy them completely. Yet new dust continues to arrive and form, creating a cycle in which the central region repeatedly manufactures and erases its own obscuring material. Radiation is equally diverse. Hot, massive stars emit intense ultraviolet light that ionizes nearby gas, while compact remnants and interacting binary systems produce X-rays. Radio waves emerge from magnetic activity, energetic particles, and ionized structures. Infrared radiation pours from warm dust that has absorbed higher energy light and released that energy at longer wavelengths. Cosmic rays and fast particles add another hidden layer, colliding with gas and influencing its chemistry even inside clouds where ordinary starlight cannot penetrate. The density of stars makes these radiation fields much stronger and more complicated than those near the solar system. A cloud may be heated on one side by a nearby cluster, compressed on another by an expanding bubble, and threaded throughout by magnetic fields guiding charged particles. This does not mean the entire center is uniformly dangerous or equally bright. Dense clouds can shield their interiors, while nearby regions may be exposed to powerful radiation. The environment changes over surprisingly short astronomical timescales as stars ignite, winds carve cavities, and energetic events disturb surrounding matter. Dust plays a double role in this system. It blocks visible light, but it also protects molecules from radiation, provides surfaces on which chemical reactions can occur, and helps gas lose heat. Radiation can therefore prevent collapse in one location, while dust allows cooling and chemistry to continue in another. The galactic center is not filled with dust and radiation because it is simply chaotic. It is filled with them because it is highly active, chemically mature, and continuously recycling matter through many physical states. What appears from afar as a hidden, hostile region is actually a complicated exchange between destruction and protection, where the same radiation that breaks molecules apart can heat dust into visibility. And the same dust that conceals the center can help preserve the ingredients from which future structures may form. The mysterious radio signals coming from the galactic center. The galactic center does not speak with one radio voice. It produces a crowded chorus of steady hums, narrow filaments, sudden flashes, and repeating pulses that often come from objects hidden at every other wavelength. Radio waves are especially valuable because they can travel through regions that block visible light, allowing astronomers to detect energetic particles, magnetic structures, pulsars, and compact sources buried deep within the inner Milky Way. Some of the strangest features are long, non-thermal radio filaments, thin glowing threads that can stretch for dozens of light years while remaining remarkably narrow. Their radiation is probably produced by fast electrons spiraling through magnetic fields, yet scientists still debate why the filaments form in particular locations, how the particles are accelerated, and whether they trace an organized central magnetic field or many smaller local events. The region also contains a magnetar, an intensely magnetized neutron star, whose pulses have helped researchers study the intervening plasma and the environment surrounding the center. Other signals appear only temporarily. Radio surveys have detected sources that brighten, fade, change polarization, or repeat on unusual schedules, sometimes without any obvious infrared or X-ray counterpart. These events are carefully compared with known objects such as pulsars, flare stars, interacting binaries, and compact remnants, but a few resist immediate classification because their timing, spectrum, or polarization does not match familiar patterns cleanly. The mystery should not be confused with evidence of artificial communication. A signal becomes scientifically mysterious when the available observations are insufficient to identify the physical source, not when the universe has abandoned natural explanations. The central Milky Way is also a difficult place to observe. Radio waves can be scattered by turbulent clouds of charged particles, making compact sources appear blurred or causing their pulses to arrive at slightly different times. Several unrelated objects may overlap along the same line of sight, and a transient may disappear before telescopes at other wavelengths can examine it. This means solving one signal often requires years of repeated observation rather than one dramatic detection. Astronomers measure polarization to learn about magnetic fields, track changes in brightness, compare frequencies, and search for repeating behavior that might reveal rotation or orbital motion. Gradually, an unexplained radio point can become a pulsar, a magnetically active star, or an unusual binary system. Others remain open questions. The galactic center therefore reminds you that discovery does not always begin with seeing something new. Sometimes it begins by hearing a pattern in the radio sky and realizing that none of the known voices fits it yet. Mystery in science is not an invitation to invent an answer. It is a precise description of the distance between a signal that is real and an explanation that is still being built. How gas can fall toward a black hole without immediately disappearing. Gas approaching a black hole usually fails to fall straight in for the same reason Earth does not fall directly into the sun. It is already moving sideways. Even a cloud that begins far away with only a modest amount of rotation carries angular momentum, and as it moves inward, that rotation becomes increasingly important. Instead of plunging immediately through the event horizon, the gas begins circling, colliding with neighboring streams, and spreading into a rotating accretion flow. Different layers orbit at different speeds, creating friction-like effects through turbulence and magnetic fields. Ordinary molecular friction is far too weak to explain the inward motion by itself, but tangled magnetic fields can connect neighboring regions of plasma and transfer angular momentum outward. Material that loses enough angular momentum can move closer to the black hole, while other material gains it and shifts outward. This redistribution is slow compared with the local orbital motion, so gas may circle thousands or millions of times before reaching the deepest region. During the journey, gravitational energy is converted into heat. Around actively feeding black holes, the gas can become so hot that it radiates intensely before crossing the horizon, meaning much of what telescopes observe is not the black hole, but matter delayed outside it. The flow can also become unstable. Magnetic fields may reconnect. Turbulence can produce temporary clumps, and pressure can launch winds or jets that remove part of the incoming material altogether. Near some black holes, the flow is dense and efficient at radiating energy. Near others, including Sagittarius A, it is thin and so hot that much of the energy remains trapped in the particles, or is carried away rather than released as brilliant light. Gas can therefore enter the black hole's gravitational territory without being guaranteed to reach the event horizon. Some is captured, some escapes, and some remains in orbit long enough to change form repeatedly. Tidal forces can stretch a gas cloud into a long stream, but this does not mean every atom follows the same destiny. The front of the cloud may experience different conditions from the back, while collisions and magnetic effects spread the material into a larger flow. Only after matter crosses the event horizon does disappearance become unavoidable from the perspective of the outside universe. Before that boundary, it can orbit, heat, glow, cool, collide, and even be expelled. A black hole is therefore not a drain with a simple downward path. It is the center of a complicated traffic system in which matter must surrender motion step by step before it can complete the fall. The delay is not a weakness in gravity, it is the consequence of motion-resisting capture. Falling toward a black hole is easy, losing every remaining way to avoid it is the difficult part. Why we still do not know what most of the galaxy is made of. The most honest description of the Milky Way's composition begins with an uncomfortable fact. Astronomers can measure the galaxy's behavior more confidently than they can identify the substance responsible for most of its mass. Stars, planets, gas, dust, and stellar remnants are made from ordinary matter, the same family of particles that forms your body and everything visible around you. Yet when researchers calculate the gravitational influence required to explain the motions of stars, satellite galaxies, and distant tracers, ordinary matter provides only a minority of the total. The remaining mass is attributed mainly to dark matter, but that name describes an effect rather than a confirmed material. Scientists know that it gravitates, gathers around galaxies, and helped shape cosmic structure, but they have not yet identified the particle or particles that compose it. Proposed candidates include weakly interacting massive particles, axions, and other unfamiliar forms of matter, but decades of underground experiments, particle collisions, and astronomical searches have produced no universally accepted detection. Modified theories of gravity have also been explored, especially because changing gravity could reproduce some galactic behavior without adding invisible particles. Yet these alternatives face challenges when applied across galaxies, clusters, gravitational lensing, and the early universe. The uncertainty does not end with dark matter. Even the ordinary matter in and around the Milky Way is difficult to inventory. Cold gas can be hard to trace directly. Hot ionized gas is extremely diffuse. Faint stars escape many surveys, and compact remnants may remain undetected unless they interact with something visible. Large reservoirs may extend into the space surrounding the galaxy, blurring the boundary between material belonging to the Milky Way and matter shared with its wider environment. Astronomers therefore combine many imperfect measurements: stellar motions, radio emission from hydrogen, absorption lines in the light of distant quasars, X-rays from hot plasma, microlensing events, and the movement of satellite systems. Each method illuminates one component while remaining insensitive to others. The result is not ignorance in the ordinary sense. Scientists know approximately how mass is distributed, how strongly it bends trajectories, and how its influence changes with distance. What they lack is the final identity behind much of that influence and a complete census of everything too faint, too cold, too hot, or too weakly interacting to observe easily. This distinction matters because a galaxy is not fully understood merely when its shape can be mapped. To understand it deeply, you must know what builds the gravitational field, how those ingredients interact, and why they exist in the measured proportions. The Milky Way surrounds you closely enough to dominate the night sky, yet most of its substance remains known through consequences rather than direct contact. You live inside a galaxy whose architecture can be traced, whose motion can be predicted, and whose total mass can be estimated, while its dominant material remains unnamed at the most fundamental level. Knowledge has reached the outline of the answer, but not the substance inside it. The faint stellar halo beyond the bright galactic disk. Far beyond the Milky Way's bright disk lies a population of stars so thinly scattered that you could travel for immense distances without realizing you were still inside the galaxy's ancient outskirts. This is the stellar halo, a vast, diffuse region containing only a small fraction of the Milky Way's stars, but preserving some of its most valuable historical evidence. Unlike stars in the disk, halo stars do not follow one shared, flattened pattern of motion. Many travel on steeply tilted, elongated, or even backward-moving orbits, carrying them high above the galactic plane and then deep through the inner regions before returning outward. Their unusual paths immediately suggest that the halo was not formed through one calm, orderly process. Some of its stars may have been born during the Milky Way's earlier stages, when the galaxy was smaller, more chaotic, and not yet organized into its present disk. Many others were probably brought in by smaller galaxies, whose stars retained distinctive motions after their original systems were disrupted. Astronomers identify these faint populations using special stellar tracers. RR Lyrae variable stars brighten and dim with regular rhythms that allow their true luminosities to be estimated, making them useful distance markers across the outer halo. Blue horizontal branch stars provide another guide because they are bright enough to be observed far from the Sun and are common in old stellar populations. By measuring their positions, chemical compositions, and velocities, researchers can reconstruct the halo's shape and discover where it becomes clumpy, stretched, or uneven. The inner halo appears more mixed and somewhat flattened, while the outer halo may be more irregular and dominated by debris from past accretion events. Its stars also tend to contain less iron than those in the disk, reflecting formation from gas that had experienced fewer generations of chemical enrichment. Yet the halo is not a smooth museum display. It contains shells, overdensities, and groups moving together, evidence that complete mixing has still not occurred even after billions of years. Some structures may be so faint that they are visible only when millions of measurements are combined statistically. The stellar halo therefore challenges the idea that a galaxy ends where its bright disk fades. It extends the Milky Way into a much quieter realm, where individual stars are rare, but historical information is concentrated. The farther you move from the familiar spiral structure, the less the galaxy resembles the object shown in photographs, and the more it resembles an archaeological field, with scattered stars acting as fragments from events too old to remember in any other form. Why globular clusters contain some of the oldest stars? Globular clusters contain some of the oldest stars in the Milky Way because many of them formed during an era when the galaxy itself was still taking shape, and their tightly bound structure allowed large parts of those original populations to survive. In the early universe, gas was less chemically enriched than it is today, and conditions favored the formation of massive, compact stellar systems in dense regions. A globular cluster could form many stars within a relatively short period, creating a population whose members began their lives at nearly the same cosmic moment. This shared birth makes the cluster valuable to astronomers because differences among its stars are easier to interpret. If most of the population started with similar ages and initial compositions, then the present distribution of brightness and color reveals how stellar evolution has progressed over billions of years. One of the most important clues is the main sequence turnoff. Stars spend most of their lives fusing hydrogen in a stable phase, but more massive stars leave that phase sooner. In an old cluster, the brightest surviving main sequence stars are less massive than those found in a younger population, because the heavier members have already evolved into giants or compact remnants. By locating this turnoff and comparing it with models of stellar evolution, astronomers can estimate the cluster's age. The faintest white dwarfs provide another clock because their cooling records how long ago the first generations of cluster stars completed their lives. Globular clusters also tend to contain very little iron compared with the Sun, indicating that they formed before many cycles of stellar enrichment had occurred. However, their ancient age is not caused simply by low metallicity. Both properties reflect formation early in cosmic history. Survival also matters. Many loose stellar groups born at the same time would have dispersed long ago, their members blending into the wider galaxy. Globular clusters endured because their stars are packed closely enough for the system's gravity to remain strong, even after losing members through stellar evolution and long-term escape. Their present population is therefore shaped by both age and selection. These are the ancient groups dense enough to remain recognizable. Some may have lost most of their original mass, and others may be the stripped central remnants of small galaxies, meaning not every globular cluster shares an identical origin. Still, the oldest examples formed within the first few billion years after the Big Bang, and carry a rare continuity from that distant period into the present. They allow scientists to study an early stage of galactic history using stars that are still alive, turning each cluster into a surviving experiment begun before the Milky Way had settled into the form you know today. The tiny satellite galaxies orbiting around us. The Milky Way is surrounded by tiny galaxies that can contain fewer visible stars than a single large star cluster. Yet they are genuine galaxies with their own histories, chemical evolution, and gravitational identities. These satellites orbit within the Milky Way's broader environment and range from the conspicuous Magellanic Clouds, visible from the southern hemisphere, to ultra-faint dwarf galaxies so dim that they were discovered only by searching for slight excesses of stars in enormous sky surveys. What separates a dwarf galaxy from a star cluster is not merely size. A galaxy can preserve stars with a broad range of chemical compositions and formation ages, showing that it once retained gas and formed multiple generations. It may also be dominated by dark matter, giving it far more mass than its visible stars alone would suggest. Ultra-faint dwarfs are especially important because some contain only hundreds or thousands of detectable stars, while moving as though they are embedded in much heavier invisible systems. Their stars are often extremely poor in iron, making them valuable laboratories for studying the earlier stages of chemical enrichment. In some cases, a single ancient stellar explosion may have left a measurable signature across much of the surviving population. The larger satellites tell different stories. The large and small Magellanic Clouds contain gas, young stars, and active star-forming regions, and their mutual interaction has helped produce long streams of gas extending across the sky. They are not simply passive companions. Their gravity can disturb the Milky Way and influence the motion of material in its outskirts. Determining which small galaxies are truly bound to the Milky Way is difficult, because their speeds and distances must be measured precisely, and some may be passing through for the first time rather than completing repeated orbits. Gaia has transformed this work by improving measurements of their proper motions, revealing that the satellite system is dynamic and less orderly than older diagrams suggested. These tiny galaxies also test theories of cosmic structure. Simulations predict that large galaxies should be surrounded by many small dark matter concentrations, but only some host visible stars. Understanding why one small halo formed a galaxy while another remained dark may reveal how radiation, supernova feedback, and the early universe suppressed star formation in the smallest systems. Each satellite is therefore more than a miniature version of the Milky Way. It is an experiment in how little matter is required to build a galaxy, how long such a system can survive near a larger neighbor, and how much of its identity can remain after billions of years under external gravity. The Milky Way may dominate its surroundings, but it is not alone. It exists inside a community of smaller worlds, many so faint that their discovery depends on noticing a few ancient stars moving together through what once appeared to be empty sky. The ancient galactic collisions still visible in stellar motion. A galaxy can erase the shape of something it consumed while failing to erase the way its stars move. After a smaller galaxy enters the Milky Way, Its original outline gradually disappears as gravity stretches its stars across vast regions and mixes them with native stellar populations. Thousands of millions of years later, those stars may look unrelated when plotted on an ordinary map, yet their velocities can expose the connection. Stars that arrive together often retain similar orbital energy, direction, and motion toward or away from the galactic center, creating recognizable clumps, arches, and folds in what astronomers call phase space, a combined map of position and movement. ESA's Gaia mission has made these patterns visible by measuring the locations and motions of enormous numbers of stars with unprecedented precision. Some groups travel on highly radial paths, plunging through the inner galaxy and then returning to great distances. Others orbit in the opposite direction from much of the Milky Way's disk. Such behavior is difficult to produce in a calm population born within the same rotating structure, so it can point toward an external origin. Chemistry provides an independent test. Stars formed inside one smaller galaxy experienced a shared history of gas enrichment, leaving patterns in iron, magnesium, and other elements that can distinguish them from stars born in the Milky Way. When unusual chemistry and unusual motion appear together, astronomers gain something close to a surviving identification tag from a galaxy that no longer exists. Yet interpreting these signatures is not simple. A pattern once attributed to one ancient collision may actually combine material from several events, and some visible wrinkles in stellar motion may be younger than previously assumed. A 2024 Gaia-based analysis argued that clearly separated folds in the inner halo could have been created by a collision less than 3 billion years ago, because much older debris should have become more thoroughly mixed. This does not erase evidence for earlier mergers. It shows that the Milky Way's history may contain overlapping impacts whose remains were mistakenly grouped into one story. Computer simulations help by showing how quickly different patterns blur, but the result depends on the galaxy's changing gravitational structure and on how accurately present motions are measured. The Milky Way therefore carries its past like water, carrying several waves at once. The original objects are gone, but their disturbances continue through the movement of what remains. By following those motions backward, scientists do not watch a perfect replay. They reconstruct possibilities from incomplete traces, constantly revising which stars arrive together and when. The deeper lesson is that history does not always survive as an object you can point toward. Sometimes it survives as a shared direction, a repeated speed, or a subtle rhythm hidden inside millions of apparently independent journeys. What the galaxy looked like when the universe was young. Rewind the Milky Way far enough, and the elegant spiral disappears before the galaxy itself does. In its youth, our galaxy was probably smaller, clumpier, richer in turbulent gas, and far less organized than the broad disk seen today. It did not begin as a miniature version of its modern form, waiting to grow larger. The first recognizable structure assembled from dense pockets of matter that drew in mostly hydrogen and helium, while small protogalactic systems formed stars and repeatedly approached, disturbed and combined with one another. Gaia measurements suggest that part of the Milky Way's thick disk had already begun forming stars only about 800 million years after the Big Bang, much earlier than astronomers once expected. That early disk would not have been thin or calm. Gas moving through it was probably highly turbulent, with strong internal motions mixing newly created elements across wide regions. Star formation occurred rapidly, dominated by environments more restless than the solar system's present neighborhood. Massive stars formed, died quickly, and began enriching the young galaxy. But the overall supply of heavy elements remained far lower than it is today. Rocky material was rarer, stellar populations were chemically simpler, and the light of hot young stars would have emphasized bright knots rather than graceful arms. Modern observations of extremely distant young galaxies help researchers imagine this stage, although none can be treated as a direct photograph of our own past. One especially revealing example observed by the James Webb Space Telescope, nicknamed the Firefly Sparkle, existed about 600 million years after the Big Bang and contains several distinct clusters of active star formation inside a small, still assembling system. Its mass may resemble what the young Milky Way had at a comparable stage, offering a possible analogue of how galaxies grow cluster by cluster rather than appearing fully formed. But the comparison has limits. Each galaxy develops within a different environment and collision history. The early Milky Way may have looked like an irregular concentration of luminous clumps embedded in gas, surrounded by incoming fragments and without the stable spiral architecture familiar today. Its sky would have been transformed repeatedly as clusters formed. Nearby systems merged, and gas settled into broader rotating structures. Over billions of years, the galaxy became more massive, chemically enriched and dynamically ordered, but it never crossed one clear moment when chaos suddenly became a spiral. The change was gradual, built from countless local processes that no single observer could have watched as a complete transformation. When you picture the young Milky Way, you should therefore not imagine a finished home under construction with the same rooms already marked. You should imagine raw cosmic material learning, through gravity and time, what kind of galaxy it was capable of becoming. How the Milky Way may eventually become a giant elliptical galaxy. The familiar spiral shape of the Milky Way may not be its final identity, but the path toward a giant elliptical galaxy is no longer considered as certain as older predictions often suggested. For decades, astronomers expected the Milky Way and Andromeda to collide within several billion years, lose their spiral structures, and settle into one larger, smoother remnant. If a major merger does occur, the transformation would be driven less by stars crashing together than by the rapid change in the combined gravitational field. Ordered stellar orbits within two rotating disks would be disturbed, sending stars onto a broad range of tilted and elongated paths. This process, called violent relaxation, can redistribute orbital energy quickly on galactic timescales, turning flat, rotating structures into a thicker and more rounded population. Long tidal tails would first be drawn outward, while some stars could be sent into distant orbits, and others concentrated toward the shared center. Gas would respond more strongly because clouds can collide, compress, and lose energy. That could trigger an intense but temporary period of star formation before stellar winds, explosions, and central activity heat, or remove much of the remaining cold material. If the two central black holes eventually formed a close pair and merged, their gravitational influence could further reshape the innermost stellar population. After repeated passages and a long period of settling, the original spiral arms might become impossible to identify, leaving an elliptical-like galaxy dominated by older stars and random stellar motions rather than one thin rotating disk. But this outcome depends on the encounter actually taking place. A major 2025 analysis combining Hubble and Gaia data found only about a 50% chance that the Milky Way and Andromeda will collide within the next 10 billion years. The motion of the Large Magellanic Cloud can pull the Milky Way away from Andromeda's predicted path, while the Triangulum Galaxy and uncertainties in the masses and sideways motions of all these systems can change the result. In many simulations, the two major galaxies pass close enough to be disturbed and later return to merge. In others, they remain separated for an extraordinarily long time. Even a merger would not guarantee a perfect, featureless, elliptical galaxy. The final form would depend on how much gas survives, the angles of the disks, the timing of repeated encounters, and later interactions with other members of the local group. The title Giant Elliptical is therefore a possible destination, not a scheduled appointment. The Milky Way's future cannot be read by extending its current appearance forward as though a galaxy were a star following one predictable life cycle. It depends on several moving systems influencing one another over timescales so long that tiny uncertainties become completely different histories. Perhaps the spiral will be erased and its stars will belong to a rounded remnant under a new name. Perhaps the encounter will be delayed far beyond earlier expectations. Either way, the form you recognize as the Milky Way is temporary. A galaxy can survive while losing the shape, structure, and identity by which its inhabitants once understood it, suggesting that continuity in the universe does not always mean remaining the same. How future astronomers may see a much darker universe. There may come a time when an astronomer looks beyond the remains of the Milky Way and finds almost no evidence that other galaxies ever existed. The universe is expanding, and observations show that this expansion is accelerating, apparently under the influence of what scientists call dark energy. Galaxies that are gravitationally bound to one another can remain together, but more distant systems are carried away as the space between them grows. Over immense stretches of future time, their light will become increasingly redshifted, stretched into longer and weaker wavelengths until many galaxies pass beyond the cosmic horizon. The distance from which signals emitted in the future can no longer reach a local observer. They will not necessarily vanish from existence at that moment. They will vanish from accessible knowledge. A civilization living in the far future may therefore inhabit a merged remnant of the local group, surrounded by an apparently empty darkness, unable to see the vast network of galaxies that modern telescopes observe. The evidence for cosmic expansion could also become harder to recover. Today, astronomers measure the motions of distant galaxies, map large-scale structure, and study ancient radiation left from the early universe. In the remote future, that background radiation will be stretched to wavelengths so long and energies so low that detecting it may become extraordinarily difficult, while stars and interstellar material could introduce noise that conceals what remains. Future scientists might still infer parts of cosmic history through careful measurements, but they would begin with a far poorer sky. From their viewpoint, the visible universe might appear to consist of one isolated galactic system surrounded by endless darkness, tempting them to conclude that the cosmos is static, local, and nearly empty. Their instruments could be more advanced than ours, while the evidence available to them is much worse. This creates a strange reversal in the story of knowledge. Humanity exists early enough to see beyond its local home, to observe galaxies at different stages of development, and to detect light that began traveling when the universe was young. The future may contain wiser observers who can no longer repeat those observations because expansion has removed the necessary information from their horizon. Darkness in that era would not mean that the universe had always been empty. It would mean that the visible record had slowly closed. You live during a rare cosmological window when the universe still allows its history to be read across the sky, reminding you that knowledge depends not only on intelligence, but also on arriving while the evidence is still able to reach you. The final stars that will continue shining in the Milky Way. The last true stars of our galactic future will not be brilliant giants, but small, faint survivors that release their energy with extraordinary patience. Low-mass red dwarfs consume hydrogen far more slowly than stars like the Sun, and many of the smallest ones circulate material through much of their interiors, bringing fresh hydrogen into regions where fusion can continue. This efficiency gives them lifetimes that may extend for trillions of years, vastly longer than the universe has existed so far. No red dwarf has yet reached the natural end of such a lifespan, so their final development must be predicted through models rather than observed directly. As the galaxy ages, the supply of cold gas available for new star formation will gradually decline. Existing clouds will be turned into stars, heated, dispersed, or locked into remnants and other objects. New stellar births will become rarer, leaving the long-lived red dwarfs to dominate what remains of visible starlight. Their planets, if any survive, would receive less energy than Earth receives from the Sun, and the habitable conditions around them could change as the stars slowly evolve. The smallest red dwarfs are expected to brighten gradually over immense periods as their internal hydrogen is transformed and their composition changes. Eventually, they may become hotter and bluer rather than swelling into red giants like the Sun, because their efficient internal mixing produces a different evolutionary path. When their usable fuel is finally exhausted, they are expected to leave compact remnants, adding to a galaxy increasingly populated by white dwarfs, neutron stars, black holes, brown dwarfs, and cold planetary bodies. Gravitational encounters over extremely long periods could disturb systems that now appear permanent. Some stars and remnants may be ejected into intergalactic space, while others move closer to the central regions or become involved in rare collisions. Yet for a very long interval, red dwarfs would remain the last steady lamps, separated by growing darkness and accompanied by objects that no longer generate their own visible light. The phrase "final stars of the Milky Way" must be understood carefully, because the Milky Way may have changed its form or merged with other galaxies long before these stars approached their endings. They would not preserve the spiral pattern familiar today. They would preserve the ancient matter that once belonged to it. Their faintness would be misleading. A massive star can dominate a region for a few million years, while a red dwarf can quietly outlast almost every structure that once made the galaxy recognizable. In the far future, endurance will replace brilliance as the defining quality of starlight. The last stars will not conquer the darkness. They will delay it, releasing the galaxy's remaining nuclear energy so slowly that a single dim sun may continue shining through ages in which nearly every familiar constellation, world and name has already disappeared. Why the Milky Way is only one temporary chapter in the life of the universe. The Milky Way feels permanent only because your lifetime is too short to watch a galaxy change its identity. It began forming more than 13 billion years ago, when small structures gathered gas, created early stars, and combined into larger systems. But there was never one instant when the complete modern galaxy suddenly appeared. Its thick disk, halo, central regions, and later stellar populations emerged through different stages, each leaving traces inside the structure visible today. The present spiral is therefore not the Milky Way's eternal form. It is one arrangement reached after a long history of internal change, incoming matter, stellar evolution, and interaction with smaller companions. In the future, that arrangement will continue to transform. The galaxy may merge with Andromeda, though current measurements leave meaningful uncertainty about the exact trajectory and timing. Even without a direct major merger, the Milky Way will keep responding to satellite galaxies, losing gas, creating fewer stars, and gradually replacing its luminous population with compact remnants. Spiral arms can fade when there is no longer enough young stellar light and cold gas to outline them. The central black hole may gain mass through occasional infalling material or future mergers, while the wider stellar population becomes more diffuse through gravitational encounters. Over far longer periods, stars and remnants can exchange energy until some are thrown away and others become more tightly concentrated. The word Milky Way will eventually stop describing a recognizable spiral galaxy, even if much of its original matter survives inside a new structure. Beyond the era of stars, the universe may enter increasingly dark stages dominated by remnants and black holes. Predictions become less certain at these extremes because they depend on unanswered questions. Scientists do not know whether protons are perfectly stable, exactly how dark energy will behave forever, or whether unknown physics will alter the distant future. Black holes are expected in current theory to lose energy extremely slowly through Hawking radiation. But for massive black holes, this would occur over timescales so immense that ordinary galactic history would be an almost invisible beginning. These uncertainties are not failures in the story. They mark the boundary where tested physics gives way to careful extrapolation. What can be stated with confidence is that galaxies are processes rather than permanent objects. They gather matter, organize it into stars, recycle it through generations, alter their structure, and eventually lose the conditions that made them luminous. The Milky Way is one temporary chapter because the universe does not preserve forms simply because conscious beings became attached to them. Its matter existed before the spiral, and much of it will continue after the spiral has gone. You happen to live during the chapter in which this galaxy contains bright arms, active stellar nurseries, planets, and at least one world capable of asking what will remain. That does not make the chapter eternal, but it may make it precious. The Milky Way's impermanence does not reduce its meaning. It explains why meaning must be found while its light, structure, and witnesses still exist.